Night moves like a quiet tide across the desert arrays, and the sky holds its breath. On a handful of distant mountains, small domes wake, shutters unfold, and glass begins to drink starlight. The algorithms hum in patient circles, measuring points that refuse to stay still, subtracting the known, sifting the common, and discarding the noise. In the middle of this ritual, a faint signature enters the field, a mote that does not belong to the deep family of our planets and comets, a traveller with the wrong curve to its path. It carries the hush of another sunrise, the chill of a chemistry born beneath unfamiliar constellations. The system that raised it is not named here. It does not send a message in any language. Yet something about its motion feels like a whispered confession. It is the new body called 3I, the third of its kind known to pass through, and the night wind seems to lean toward it as if listening. It crosses the dark like a coal adrift from a distant hearth, not firing its engines, not steering, only accepting the gravity that meets it. The numbers that define it are simple and profound. The curve of its orbit opens outward, rather than closing back upon itself. The speed with which it falls toward the sun refuses to bend enough to keep it captive. In the slender vocabulary of celestial mechanics, one symbol tells the whole story. Eccentricity greater than 1 means a bridge from beyond, a path that does not loop, a visit rather than a homecoming. No certificate is stamped, no ceremony observed, only this quiet metric, and the sky nods. Long before it grows bright enough to snare the unaided human eye, the new visitor begins to breathe. The breath is not air. It is a fragile haze of volatiles stirred by sunlight, a thin perfume of what was frozen inside it during a childhood far away. In the records of previous wanderers, the first exhales tell stories about origin. Some reveal water that flashes into steam as warmth returns. Some give off other ingredients that wake earlier and fade later, depending on how tightly the ice was packed, how long it slept between the stars, how the dust above it learned to hold heat and shun it. The newcomer carries this same promise of a chemical diary, a page that turns in the faint coma around its heart, written in lines that telescopes can read. Heard at human scale, its arrival is almost nothing. No thunder, no scrape, no warning. Yet the instruments feel the tremor in the data, and a community that has waited since the last interstellar surprise tightens its circle of attention. In quiet offices and late kitchens, observers adjust schedules and ask for time on mirrors that can peel spectra from a smear of light. The object itself does not hurry. Across the months it will lean sunward, grow, and tilt a pale tail along the solar wind, then veer away into a thinner night. Its stay is short, but for a while it moves within reach of the most attentive questions humans can assemble. There is a particular wonder in the third occurrence. The first interstellar object taught astonishment. The second taught patience and comparison. The third promises pattern. A single ember is a miracle. 2 are coincidence. 3 begin to sketch a furnace somewhere beyond the hills, a process that throws sparks into the grasslands of the galaxy. Planetary systems form from cloud and rotation. They jostle, they collide, they tidy themselves, they ship their debris outward with the quiet efficiency of gravity and resonance. Somewhere in that long housekeeping, an iceberg, a shard, a sliver of mantle is lifted away and set adrift. For ages it wanders through the thin country between stars, its surface changing by dust storms of radiation, its interior keeping the memory of a birthplace that cannot be seen. Then it crosses the sun's light, and becomes a story that can be told. The human imagination reaches for metaphors when it meets this kind of distance. It imagines a bottle, in a current, and some message inside, burned and nearly unreadable, but still shaped by a hand. It imagines a traveller stepping into a town where no one knows its name, taking a single slow walk along the main road, and leaving without a farewell. It imagines an ember that carries the heat of a hearth that has long since fallen quiet. These metaphors do not measure or prove. They do not replace the discipline of photometry and spectroscopy. Yet they are invited because the subject itself is a citizen of metaphor, a bridge between star and star, a material fact that glows like an allegory. The night accepts both, the poetic and the precise, and asks them to sit together for a while. When the visitor brightens, the phase angle ticks upward, and the geometry of reflection begins to sculpt a personality from light. Grain by grain, dust learns to point or retreat. Some arcs of the tail appear to lean where no tail should lean. Some jets open like fans. Some remain buried and quiet. Rotation lends rhythm. The light curve will rise and fall with a beat that suggests shape or tumbling, a spindle or a shard, a dance taught by collisions long ago. Each small modulation in brightness incubates a hypothesis. Smooth faces reflect differently than rough ones. Layers insulate and crack. Sometimes the dominant ice waits deeper than expected, held beneath a rind that space has cooked for 1,000,000 winters. Sometimes the early breath is not the one familiar comet's release. Each possibility is an invitation to the next observation. Earth, while immense to those who live on it, is small to a visitor on a line like this. The object will not touch the atmosphere. It will not graze the moon. Its influence will be a gift of meaning rather than momentum. Children will hear its name and tuck it beside the earlier ones, building a new family of the known unknowns, a brief index of the galaxy's scraps that happen to pass close enough to catch. Somewhere a teacher will draw a hyperbola on a whiteboard and circle the open arms of the curve, explaining that some paths never close, that some goodbyes are written into the first hello. Somewhere a poet will write that the wind tonight smells like dry ice and tin. Somewhere a scientist will refresh a terminal window and watch a spectrum resolve into lines that say more than the poet dared. This is not a monster in the sky. It is not a sign of harm. It is a question that has been given a body, a riddle clothed in ice and dust. The physics that govern it are the same physics that bend the orbits of planets and steer the tails of comets. Newton would recognize the pull, Einstein the slow curvature of the path, the wind of photons and ions that shape the hair-thin filaments near the head. It is a simple thing, and it is immense. It is small enough to vanish behind the width of a thumbnail at arm's length, and large enough to tilt conversations on Earth toward the outer darkness, where beginnings are still being negotiated. He stands nowhere in particular, this narrator who describes it. He speaks from observatories and from kitchen tables, from scrublands and from library stacks where old sky catalogues sit under dust. He speaks from the hum of a mount tracking at sidereal speed, from the hush that falls in the seconds between exposures. He sees the raw frames, the streak of a satellite that intrudes, the glow of city air that must be removed pixel by pixel. He sees the subtraction, sees the stranger remain after the familiar has been taken away. He sees the list of candidates collapse to one, with the wrong speed and the right angle. He sees the confirmation, muted and electric, travel through a community that knows how rare this is. The night accepts the newcomer without a sound. The planets keep their time. The sun continues to pour out the same light. Yet the narrative inside human minds changes. A third visitor means a wider exchange is underway, that interstellar space is not empty of small personal things, that systems speak to one another in the currency of lost stones and thawing ice. It means that formation is a little messier than hoped, that ejection is as natural as capture, that belonging is sometimes temporary. It means, too, that a hand extended across a void is sometimes answered by a passing palm that does not stop, and still the touch matters. By the time dawn dilutes the desert, the domes are closing. The data sleeps on servers and in notebooks, in small jokes written at 3 a.m, in silent graphs that will grow teeth and voice in coming days. The traveller continues along its line, through the solar wind, indifferent to being seen, generous in the way of objects that cannot help but reveal themselves under light. It carries an aroma of unfamiliar frost, a colour the instruments will argue about, a pattern of breath that may reward a long stare. It will leave. It will not return. The sky will keep a memory of the night when it arrived, and humans will keep a question warmed by the friction of thinking. The search began long before anyone named the visitor. In a high valley where the air thins and the ground keeps its own counsel, the Atlas telescopes kept their patient schedule. 4 times a night, the same fields were swept, and 4 times a night, the machines compared each fresh frame against the sky that existed the night before. In the language of survey work, subtraction is a kind of revelation. Fixed stars cancel. Ghosts of faint galaxies dissolve. The survivors are the living things of the moment. A flare on a distant dwarf, a new supernova, a satellite that barges across the field, an asteroid that drifts like punctuation through a paragraph of light. On one of those runs, a point moved with just the wrong kind of ease. It was not fast enough to be a near satellite, not slow enough to be safely bound. The pipeline circled it and drew a quiet box. The process that followed was as old as systematic astronomy and as new as this year's code. The software grouped the moving dots into tracklets, tiny arcs made of minutes. A preliminary orbit rose from these crumbs, the way a musician hears a key signature after only a bar or two. Observers on duty checked the quality flags and the residuals, because even beautiful arcs can lie when clouds have slipped through or a hot pixel has masqueraded as a star. The coordinates and times were pushed to a message queue watched by people in every time zone. A brief, clinical note marked the candidate as interesting, the kind of word that carries more weight in science than it does in conversation. Within hours, telescopes elsewhere turned. The Minor Planet Center received astrometry with careful uncertainties, each position measured against catalogues that had been scrubbed of bias. A preliminary designation went live, a string of letters and numbers that looked more like a password than a name. The solving engines then began to fit an orbit through the points and report its shape. Eccentricity edged past unity, and then stayed there as more data arrived. Solar elongation remained tolerable, which meant that the world still had a window before the glare would swallow the line of sight. A brief note rippled through observatory mailing lists and private channels. This one was not like the ordinary quarry of the night. The southern facility had done the first lifting, and that mattered. From that latitude, the camber of the Milky Way ran like a road across hours of darkness, and the target lay in a part of sky that the northern sights could not chase until later. Weather cooperated with a patience that felt out of character for mountain climates. Seeing was modest but stable. The survey cadence held. Bit by bit, the confidence intervals shrank. Each additional tracklet did what gravity promises it will do when measured well. It brought clarity. The plane of the orbit was nailed down. The inbound speed, once a blur behind large error bars, stepped into focus. The formal parameter that marks a visitor, the hyperbolic excess velocity, no longer hid inside uncertainties. It was real, not a numerical mirage thrown up by bad geometry. Photometry arrived in the same breath. The first night suggested a magnitude brighter than a bare rock would offer at that distance, which meant activity was already awake. Colours in standard filters leaned toward a gentle red, a tone familiar from objects that have spent long eras in cold radiation. But the slope was a nuance still in debate. Aperture corrections and 0 points were argued over, with the calm intensity of colleagues who know that small errors, multiplied by distance, become large misunderstandings. An early estimate of the absolute magnitude settled into the spreadsheets, tagged provisional, ready to be replaced as soon as better nights cooperated. Follow-up came from everywhere. A long string of modest telescopes tracked non-sidereally, holding the visitor still while the stars slid by as streaks. The trick buys depth under indifferent skies, and it buys data from communities often left outside the headlines. A smaller cadre used larger mirrors to pull spectra out of the thin coma. The earliest results were low resolution and pragmatic, simply a way to test whether the light was dust-dominated or gas-heavy, whether broad features were hiding beneath the continuum like reefs beneath water. Each team reported to the clearinghouse, and the record grew. Naming followed the rules. Interstellar status must be demonstrated, not assumed. Once the case became robust, the designation shifted to the small family that now exists for such bodies. A letter that stands for interstellar fixed itself to the number 3, a count of a club still new enough to fit inside a single breath. The discoverer credit leaned toward the survey that caught it, the way tradition asks, acknowledging a system that has learned how to turn nightly routine into first sight. The new tag sounded compact and clear, a reminder that even romance in astronomy travels by way of bureaucracy that knows how to be fair. The story of where is not only a latitude and a mountaintop, it is also a culture of vigilance. Atlas was built for danger closer to home, a late warning system for rocks that wander too near. To serve that mandate, it watches wide and fast, and in that wide net the universe tends to throw extra gifts. The wide-field lenses drink large squares of sky at a time. The detectors gather millions of pixels that will be reduced to a few numbers for each source, and the code subtracts the known until a handful of novelties remain. Most novelties are unromantic. This one was not. The same architecture that made it possible to warn cities also made it possible to greet a traveller from between stars. How this is done feels straightforward only after it has been mastered. Telescopes track at sidereal rates that match the movement of the sphere. At survey cadence, the field is imaged 4 times, separated by minutes. The moving object processing sorts by motion and direction, flagging streaks and points that shift consistently. Spurious detections from cosmic rays, scattered light, or low Earth orbit intruders are pruned. The survivors are tested against ephemerides for known asteroids and comets. What remains after this pruning earns the time of human eyes. Short arcs feed a solver that fits orbits from mere hints. Inbound speed beyond the reach of parabolic motion sets off quiet alarms. Everyone involved keeps a steady tone, because sky work punishes excitement. The rules of attention are simple: measure, confirm, share, repeat. The confirmation step is where a community becomes visible. A robotic dome opens in the south and sends its share. A 2-meter instrument in the north carves a spectrum from a smear of light near the noise floor and teases out a line that might be real. An amateur in a city fights sky glow and proves that even in a pale dome the target can be captured if the tracking is honest and the calibration is stubborn. A team in the west checks a light curve for rotation hints but refuses to publish a period until the coverage gains a second night. Another team preloads a program for a space telescope, ready to ask for a rapid target of opportunity if the queue allows. All of this happens without ceremony, because routine is the only ritual that works at speed. When did all this begin is answered in calendar language that never quite fits the feeling of discovery. The week carried the heat and dust of a southern winter and a northern summer. The moon's phase was forgiving. The sun set on schedule and rose on schedule, as if the night were not electrified by a new idea. The timestamps in the logs traced the same sequence that has always marked first sight in modern astronomy. One night to flag, the next to confirm, a handful more to lock in an orbit clean enough to speak. There is an elegance in that tempo. It is slow compared to the velocity of headlines, but it is fast enough to keep pace with a body that will not linger forever in easy geometry. The meaning of how is technical, and it is also human. Instruments do not hallucinate, but people can, and so the process is built to temper hope with measurement. The poet in the room never gets to touch the keyboard until the arc length doubles and the residuals go quiet. The instruments are placed in deserts and high plateaus not because romance lives there, but because the air is thin and the clouds are rare. The code is audited by colleagues who dislike surprises. The data is shared publicly according to rules that came out of long arguments about fairness and speed. The name arrives last, after the mathematics are satisfied. What arrived on those nights was a stranger that fit the sky and did not fit the household customs of our own system. The opening act was the discovery itself, the quiet rectangle around a moving point that should not have been able to stay. By the end of the first cycle of measurements, an object with a foreign claim on space had received a record in the ledger. The ledger is dry and necessary. The feeling it concealed was not. The observer on duty smiled toward an empty dome and wrote a single note in a log that no one else would ever read. It said only this: found. A single parameter changes the story of a path. Eccentricity names the shape, and with that name, it names the fate. When the number is less than 1, the traveller is held by the Sunday. When it equals 1, the path is a parabola that brushes the edge of freedom. When it rises above 1, the curve opens and never closes. Energy changes sign with this crossing. The specific energy per unit mass becomes positive. The figure of the orbit becomes a hyperbola, and the conclusion is plain. The sun can bend the motion, it cannot keep it. The mathematics looks clean on a board. On the sky, it arrives as a set of points measured against background stars and folded into an answer that refuses to loop. The method is patient. Observers measure where the speck sits at minute and hour offsets, apply corrections for atmospheric refraction and optical distortion, and tie the coordinates to catalogues that have already been corrected for subtle biases. Each timestamp brings a small slice of the orbit into view. A solver ingests these slices and fits a conic with the least squares compromise that gravity demands. The orbit elements settle into clarity as the arc length grows. The covariance shrinks. The confidence that eccentricity truly exceeds 1 rises above the level where caution lives. Barycentric calculations replace the simpler, heliocentric versions, because the sun itself does not sit fixed. The wobble of the solar system's center of mass can nudge a borderline case into confusion if it is not respected. With the proper frame selected, the sign of the energy remains positive. The verdict holds. A hyperbola carries its own language. Semi-major axis becomes negative, a reminder that the old habits of bound motion no longer guide intuition. The parameter that observers love to quote appears: the hyperbolic excess speed. It is the velocity the traveller would still hold if the sun faded to nothing at infinity. Bound comets do not have this luxury. They slow, they turn, they belong. An object with a non-zero excess speed ignores that script. It enters with more kinetic energy than the sun can absorb, spends a brief season near the light, and then leaves with the same surplus intact. The shape is not an ornamental difference. It is the geometry of a decision already made far from here. Skepticism is built into this work, and it serves a purpose. Not every curve a solver returns is the truth. Planetary encounters can pump an orbit, and some comets leave perihelion on paths that momentarily exceed unity before fading back toward the long crawl of a weakly bound ellipse. A careful analysis asks whether gravitational scattering inside the planetary zone could have created the same signature. The answer depends on timing. If the inbound track is already hyperbolic before any close approach, the case for a foreign origin strengthens. The Tisserand parameter with respect to Jupiter is checked as a companion test. Values that defy the familiar ranges for long-period comets are a second flag that the traveller did not grow up under the same household rules as the usual visitors. Data find their power in accumulation. With each night, the asymptotes of the hyperbola sharpen. The inbound direction in celestial coordinates fixes itself to a narrow patch, which then becomes a seed for deeper questions about galactic kinematics. The outgoing direction tilts away at a predictable angle set by the impact parameter, the speed at infinity, and the weight of the Sunday. The scattering angle refuses to collapse into the gentle curve of a near parabolic graze. The timeline becomes clear. Entry from the outer darkness, acceleration in a steeper well than it has seen in eons, swing by the focus that rules this system, and departure toward a sky that holds no orbit for it to rejoin. Light alone would not prove such a story if the forces on the body were extravagant. Non-gravitational accelerations can mimic or distort. Outgassing can nudge a nucleus the way a faint thruster would, and radiation pressure can shift small grains dramatically. Analysts therefore fit additional terms to the equations of motion, terms that describe recoil from sublimating jets and gentle pushes from sunlight on the cross-section of dust. When those terms are included and the hyperbola remains, the confidence grows. When the same answer appears in independent pipelines, some run by survey teams and some by small groups with their own code, the confidence becomes a floor rather than a ceiling. The shock lives not in the arithmetic, but in what the arithmetic implies. A hyperbolic orbit is a confession that the quiet inner order of the solar family is not a closed room. The sun is a negotiator rather than a jailer. Objects arrive with histories written under other lights, and the system can only edit those histories, not erase them. Long-period comets from the distant cloud come close with eccentricities that scratch at unity from below, heirlooms that the sun can still call its own. An interstellar body crosses the threshold and refuses adoption. The difference looks small when written as numbers on a line. In space, it is the shape of a promise that will not be kept. There is a precision hidden inside the poetry of a hyperbola. One can draw the path on paper and see that it belongs to the family of conics, with two branches that face away from one another and a focus where the sun sits like a bright punctuation mark. The object enters along one asymptote, leaves along the other, and the two lines trace the way infinity itself looks in this geometry. The closer the trajectory passes to the focus, the more the line of travel is bent. With a high excess speed, the bend is modest, a quick nod rather than a bow. With a lower excess speed, the deflection becomes deeper, the time spent in the inner system a little longer. Yet the essential fact remains. This is travel, not residence. Even at this level of abstraction, the details of measurement matter. Light-time corrections transform coordinates from where the object was when the photons left to where it is when the calculation speaks. Planetary perturbations are included through ephemerides that carry the gravities of the major bodies and the subtler pulls of the larger asteroids and the flattened mass of the Sunday. Relativistic tweaks help keep the residuals honest at the innermost parts of the path. Photometric information enters as a parallel story that tells how the coma and dust might complicate centroiding, and therefore the derived positions. A good solution is not a single, elegant equation. It is a web of careful small things that together support a conclusion sturdy enough to carry meaning. To call this a shock is to admit a habit of expectation. The night sky feels serene to the human eye, and the mechanics of familiar orbits reinforce that calm. Planets trace reliable ellipses. Periodic comets return with the predictability of old friends who send postcards. Long-period comets remind the system of its own deep reservoir of ice. A genuinely interstellar visitor interrupts that rhythm. The event demands a different mental map. Space between stars is not barren. It is a quiet highway for debris, ejected by young systems that reshape themselves violently and then calmed. Each hyperbola seen near the sun is a page torn from a distant book. The angles and numbers, once accepted, generate practical consequences. A hyperbolic inbound path dictates the range of solar distances the object will reach and the rate at which those distances change. Instruments must be scheduled to meet a moving window. A fast excess speed grants little time for high-resolution work near closest approach. A trajectory that stays far above or below the plane of the ecliptic challenges observatories in certain latitudes. The geometry of a hyperbola writes an observing plan as clearly as any proposal could. The plan is brief. The object will allow a handful of weeks for the deepest questions, and then it will recede into the thin country again. There is a deeper silence in the hyperbola than in the ellipse. An ellipse implies return. A hyperbola refuses. That refusal is not cruelty. It is simply the arithmetic of energy in a universe that allows encounters without captivity. The sun is immense, yet even the sun cannot keep what arrives with enough speed. The proof fits inside a small suite of parameters that any student of celestial mechanics can write. The feeling of it does not fit so easily. It feels like a wind through an open door in winter. It feels like a train that does not stop at the platform, only lets its light cross the faces of those who wait. By the time the parameters are written cleanly into the record, the shock has settled into purpose. The curve that breaks the household of orbits becomes the teacher of questions that only an outsider can ask. The sky has shown the shape that does not close. The mind adjusts. Observation turns from weather to what? from the shape to the substance riding that shape, the hyperbola has done its first work. It has reminded the system that openness is part of its nature. First light arrives as a calm unveiling. The object is centered on a detector that knows the taste of faint things, and stars around it sharpen into pinned grains. The frame looks ordinary until a closer look at the target reveals a softness that a bare rock would not wear. The center is tight, but it is wrapped in a faint vapor, a teardrop laid delicately against the black. That geometry matters. Dust does not arrange itself by accident. Sunlight, solar wind, and the slow push of radiation pressure sketch a direction on every image. The coma points gently away from the sun, yet a bright fan also leans toward it, as if large grains heavy with inertia are escaping in a direction that intuition would not choose. Deconvolution begins. Observers fit a model point spread function to nearby stars and subtract it from the nucleus to separate the unresolved core from the envelope. The residuals refuse to vanish. The light that remains is not a crisp point. It is a shallow gradient, brightest at the core and then dropping roughly as inverse distance from the center, the hallmark of a steady dust fountain. That radial slope is a familiar signature of comae that have had time to establish flow, and it assures the teams working in the dark that they are not staring at a misbehaving asteroid. A live coma means sublimation is already awake at a heliocentric distance where water ice would be lazy. Photometry anchors the aesthetics in numbers. Apertures of increasing radius are placed on the head. Background is computed in rings that avoid field stars, and the flux is transformed into a magnitude that can be compared between nights. The proxy that comet workers favor, AF rho, is calculated to remove some of the dependence on aperture and seeing. The value is modest yet rising, the kind of trend that says dust production is not a burst but a growing habit. Translate this number into a mass loss rate and the estimate ranges broadly, since albedo and grain size must be assumed, but the scale lands comfortably within tens to hundreds of kilograms per second of dust. For a small nucleus, this is a spirited output, and it means that even a few square kilometers of active patches could power the display. Color adds its quiet hint. Broadband measurements show a reflectance slope slightly redder than sunlight, a trait shared by many cold surface populations that have spent long years under radiation. The slope is not extreme. It suggests grains that carry organic crusts or irradiated mantles, yet it does not speak of anything exotic. Spectra at low resolution, taken to beat the clock rather than to win beauty contests, show a continuum that dominates. Gas features are weak or absent at the earliest attempts, which may be an artifact of sensitivity or may be a genuine clue. A dust-heavy coma under a modest gas flux aligns with a scenario where a volatile more eager than water lifts grains early, then sunlight does the rest. The nucleus itself remains hidden, yet not entirely untouchable. By modeling the coma profile and extrapolating the central point that would be present if all fuzz were gone, observers can set an upper limit on the true solid body. The algebra yields a radius that fits inside a handful of kilometers, smaller if the albedo is bright and larger if it is dark. The uncertainty is honest, because coma light still drowns the point source. Even that limit teaches. A small nucleus producing an extended, coherent coma is not an oxymoron. It is a sign of volatile reservoirs accessible to cracks and sunlit rims that focus heat into microclimates. It also hints that rotation could modulate activity in ways photometry might reveal once the coma quiets, if it ever does. Structure within the coma is the next arena. Enhanced images, stretched and filtered to bring out low-contrast features, reveal a subtle sunward fan edged by faint streamers that curve anti-sunward downstream. Analysts lay synchrones and syndines across the frames, the families of curves that trace dust released at specific times and with specific beta values, where beta measures the tug of light against the pull of gravity. The best overlays suggest a dominance of relatively large grains, ones for which radiation pressure is gentle. That choice of grain sizes would explain the sunward feature. since heavy particles launched from vents can travel up sun before the slow push of light herds them back. It would also explain a tail that looks fat and stubby rather than long and needle-thin. Phase angle turns out to be a hidden sculptor of mood. As the line between sun, comet, and Earth changes, the coma brightness can surge under forward scattering. Small grains act like tiny mirrors when viewed at small angles, and even a modest change can goose the magnitude. Observers correct for this with standard phase functions, but the truth is messier than any table. Varied grain sizes and porous aggregates bend light in ways not perfectly captured by simple laws. The images, however, remain honest. They keep showing a head whose shape leans toward a teardrop, a brightness gradient that looks orderly, and a tail that respects the antisolar vector while allowing sunward expression. Time series work begins as soon as hardware allows. Short exposures taken back-to-back for an hour or two probe for periodicity. The amplitude is small. A coma dilutes rotation signals like fog softens a lighthouse beam, so the faint rise and fall could hide almost anything, from a slender spindle to a squatter body. Tumbling is not excluded. Non-principal axis rotation tends to smear light curves near the noise floor, and small interstellar bodies are good candidates for rotational states that were never tamed by tides. Only patience can sort that out, and patience is paid for with long nights when weather cooperates. The gas story refuses to stay quiet. Targeted narrowband imaging tuned to common emissions tries to sniff out CN, C2, and other familiar ghosts, and the first constraints come in as upper limits that still allow comfort for CO or CO2 doing the early lifting. High-latitude sites, with stable near-infrared air, search for rovibrational lines that betray the more volatile ices. Some recoveries flirt with significance, then retreat when systematics are better understood. No one is discouraged. These are the very early days of a sprint, and reality often feels like a rumour before it becomes a number on a plot that everyone can reproduce. The first space-based portraits are the most merciless. Seeing does not blur them. Starlight pins itself to diffraction spikes, and the coma reveals its true radial soul. In such frames, the inner arcsecond of dust is resolved for what it is, a fountain shaped by vent geometry, rotation, and sunlight. Subtle asymmetries become unarguable. A brighter quadrant on the sunward limb suggests one or two active regions rather than a uniform exhale. Jets are hinted at, not as dramatic corkscrews, but as gentle fans whose footprints remain stable over the hour-long visits a space telescope can afford. From these fingerprints, one can back out constraints on pole orientation and active latitude, though the solution space remains large. Thermal modelling joins the conversation. The heliocentric distance at first light, the activity level implied by AF rho, and the absence of strong water lines together point towards CO2 as a plausible driver. Carbon dioxide sublimates efficiently in regions where water would sleep, and it can loft dust without leaving a strong optical gas signature. If the crust has been processed by radiation into an insulating skin, subsolar cracks become the essential pathways. Heat diffuses inward by centimeters to decimeters. Volatiles reach vapor pressure, and jets worm their way toward daylight. The nucleus does not need to be large to support this. It needs floors, and floors are plentiful in small icy rock. The images reshape practical plans. If dust is dominated by larger grains, spectrographs that chase gas must work harder, but images can map structure deeply. If the nucleus is small, attempts to separate its light from the coma must exploit high phase angles and the sharpest optics. If jets are stable, long slits can be aligned to ride along features and measure velocity fields. The first light does not answer questions. It allocates resources. Time on mirrors is precious. The sky gives a hint about where to spend it. Public eyes see the same frames that specialists study and find their own truths. A grey teardrop on a dark field looks simple and elegant. The stillness of the starry background contrasts with the implied motion of the visitor, and the irony pleases. Viewers notice the sunward fan even without knowing the word. They notice the tail that seems to hesitate, They notice the pin at the center that may or may not be a solid thing. Wonder does not require calibration. It requires a picture that lets the mind step closer. The first light turns a rumor into a body and a theory into a texture. A curve on a plot is replaced by an image that shows how material behaves under heat and light. A tea-colored slope in a spectrum is replaced by dust that can be imagined as grains, shards, and clumps. With that conversion complete, the questions gain muscle. How deep are the vents? How quickly do they migrate with the subsolar point? How many square meters of active terrain are required to support the measured dust? How small can the nucleus be and still give what the coma demands? The early images do not resolve these unknowns. They make the unknowns vivid. The first full breath arrives as infrared light drawn into prisms and laid out as a ladder of narrow valleys and hills. Across that ladder, a particular trough deepens with quiet certainty at a wavelength that chemists know by heart. Carbon dioxide speaks there with a fundamental vibration that no dust can mimic. The same panels that show this voice keep a searching eye for water's signature and find it hesitant, a slope rather than a shout, a trace rather than a chorus. Carbon monoxide tests the air with its own line and shows only a narrow presence. The conclusion is not a trumpet blast. It is a calm accounting. The gas that wakes first and strongest is carbon dioxide, not water. Chemistry determines which ices can lift dust at a given distance from the sunday. Water asks for warmth that is not yet present. Carbon dioxide asks for less. Its vapor pressure rises at temperatures that still feel like deep winter, and it can carry grains from sheltered fissures where heat gathers by day. A coma driven by carbon dioxide explains why the earliest images look full and busy, even when the heliocentric distance remains unfriendly to water. It explains the fan that can lean sunward when large grains exit a vent with enough momentum to ignore radiation pressure for a time. It explains a tail that seems stouter than the needle shapes often sketched by comets, served primarily by small, easily pushed grains. This balance between gases carries the weight of history. If water waits while carbon dioxide races ahead, two stories compete for the credit. One story says the nucleus grew in a region of a protoplanetary disk where carbon dioxide ice was abundant and water was either scarce or buried beneath layers that do not communicate quickly with the surface. Another says the surface has been cooked by long exposure to cosmic rays and ultraviolet light, turned into a dark insulating rind that cages water deeper down while leaving carbon dioxide closer to the skin. In both stories, the same observation takes on different meanings. A spectrum is a mirror for origins and a witness to aging. The ratio of one molecule to another is the handwriting of that testimony. Thermal models are the tools that translate this handwriting into pictures of the unseen. A small body with low thermal inertia lives by a rapid cycle of day and night, its skin warming and cooling while the interior barely notices. A small body with higher inertia carries heat through dusk and into darkness, and cracks that face sunrise become privileged paths for vapor. A crust only decimeters thick can isolate water locked beneath and still let carbon dioxide reach the sunlit air. The thermal skin depth at these distances is measured in centimeters to tens of centimeters for realistic materials. That modest depth is enough to turn a nucleus into a puzzled tea kettle, whistling along etched seams while a colder reservoir sleeps. Dust reacts to this engine with stubborn pragmatism. Large chunks respond to gravity and initial kick. Fine grains surf on light. If carbon dioxide dominates outgassing, the mass loading can be different than in water-rich flows, since fewer molecules moving faster can achieve the same momentum transfer to grains that must be lifted. Dust-to-gas ratios inferred from broadband photometry are compatible with this interpretation when they tilt high. The coma takes on a look that is less gossamer and more granular. Even the way the brightness fades with distance from the head can reflect this, since heavier grains stay near their launch tracks longer before sunlight shepherds them into the classic tailward sweep. Rotation makes the gas engine a chime with a beat. As vents move across daylight, carbon dioxide jets turn on and off with the clock of the nucleus. The pattern they etch in the inner coma becomes a field notebook for modelers who use synchrones and syndynes to reconstruct the launching times and sizes. A pole tilted toward or away from the sun alters the duty cycle of individual vents and concentrates activity into certain latitudes. The absence of strong water lines encourages the idea that only specific belts or cap-like regions are currently breathing. Persistent asymmetry in the head supports that thought. Each of these threads strengthens an image of a worldlet whose machine room is small and focused, rather than widespread and mellow. The surprise is philosophical as much as technical. In the inner system, water is the usual architect of cometry display. It sculpts the coma, it drives jets, it drags dust, it draws bright bands across spectrographs. A visitor whose first language is carbon dioxide asks for a revised hierarchy. That revision connects to ideas about disk chemistry. In the warm regions inside a young star's water-snow line, dust compacts and water condenses selectively. Farther out, the carbon monoxide snow line defines a colder land. Carbon dioxide sits between those realms. It can be born as a primary condensate in that middle territory. It can also be synthesized when ultraviolet photons or energetic particles rearrange the bonds in mixed ices that contain carbon monoxide and water. Either path yields a surface that looks ready to speak in the infrared, long before water can do more than whisper. Isotopic ratios become a quiet obsession once the primary carriers are identified. A careful spectrum can separate the small frequency shifts that mark heavy isotopes. Deuterium in water, compared to hydrogen, speaks of the thermal history of the birthplace. Carbon and oxygen isotopes inside carbon dioxide point to processes in the parent disk, from inheritance of cloud material to chemistry on grain surfaces. Even modest constraints become maps when plotted against what is known of solar system comets. If the ratios cluster near familiar values, the story leans toward universal chemistry operating under similar conditions in many young systems. If they stray, the case for a different cradle strengthens. Non-gravitational forces become a second arena where carbon dioxide leaves fingerprints. A nucleus ventilated asymmetrically feels a steady thrust that adds or subtracts a whisper of velocity. The effect is small in absolute terms, yet large enough to be measurable in precise orbit fits when data span weeks to months. Because carbon dioxide can remain active at greater distances, this thrust can act over a longer arc than a water-dominated scenario would permit. A prolonged, gentle push shifts the perihelion time and distance by tiny amounts and, with luck, changes the spin state as well. Torques from directed jets can nudge a tumbling object toward or away from principal axis rotation. Light curves that slowly change behave like seismographs of such evolution. Mineralogy hints ride on the gas. Carbon dioxide brings with it the potential to drag organics and prebiotic fragments from fractures where they have been shielded from the harshness of interstellar space. Spectra that show broad features from complex organics in the near ultraviolet or visible would strengthen that link. Polarimetry can contribute by measuring how light scatters off grains that carry different textures and coatings, because organics tend to change the polarization curve. A coma organized by carbon dioxide outflow could distribute these grains differently than a water storm would, biasing measurements towards certain scattering angles and confusing naive comparisons. The result is not a tidy narrative. It is a network of observables, where each node depends on and affects several others. There is a question that hangs over the carbon dioxide diagnosis like a star above a road. Why is water shy? If a rind exists, how thick and how old is it? If processing produced it, do we expect a sudden boil of water later as the crust fails or thins under stress? Or will the visitor remain a carbon dioxide machine throughout its stay? These choices matter for planning and for understanding. A late-blooming water coma would alter hazards for spacecraft observations and change the balance of dust sizes that extend the tail. It would also reset inferences about the interior architecture, since a reservoir that wakes suddenly is not the same as one that never existed or has been exhausted beyond recovery. Practical work follows from these reflections. Telescopes with mid-infrared capability are prioritized to watch the carbon dioxide lines evolve with solar distance. Near-infrared instruments are tuned to check water at every opportunity, since even a small rise would change the meaning of the dust. Millimeter arrays look for neutral organics that link to carbon dioxide production. Thermal imagers try to pin down the size and albedo of the nucleus by catching its own heat beneath the coma's glow. Each facility fills a blank in a puzzle that was drawn the moment the first spectrum chose its allegiance. In the story told by this chemistry, the universe does not present a simple ballot of yes or no. It offers ratios and thresholds and delayed awakenings. Carbon dioxide has stepped onto the stage as the lead. Water waits in the wings or sleeps in the cellar. The audience of instruments notices and adjusts, trading nights and recalibrating expectations. The little body at the center does not change its mind. It is only what it is. Yet by revealing which gas finds its freedom first, it invites thoughts about disks and distances, about winters measured in millennia, about crusts that keep secrets with real skill. The mystery grows not because the signal is faint, but because the clarity points to many credible pasts, each with a different map drawn on the same cold stone. The spectrum opens like a music sheet, dense with tiny notes, each line a narrow voice excited by sunlight and released into darkness. Through that forest, a set of signatures stands out with a grace that is almost severe. They belong to neutral nickel. The pattern is too coherent to mistake, and it repeats with the steady elegance that only atoms possess when they scatter radiation in free space. Iron is searched for in the same frames with the same care, yet iron refuses to answer with equal strength. The imbalance is not a trick of noise, not a quirk of calibration, not an artifact of a cloudy night that muddled the continuum. It is a chemical fact written in light. High-resolution instruments resolve the lines into their delicate spacing. The profiles are narrow, centered where they should be once Earth's motion has been removed. Telluric features are modeled and subtracted. Solar absorption imprinted on the reflected continuum is accounted for. What remains are emission features pumped by the sun and fluorescing in the near vacuum of the coma. The line fluxes, when integrated, give column densities after a careful dance through G factors that describe how the solar spectrum excites each transition. This is not guesswork. Atomic physics supplies the constants, and the constants conspire to produce a clear tally of nickel atoms in the beam. Nickel without iron is a puzzle because the cosmos does not build them so far apart. In bulk matter forged in stars, iron dominates by number, and nickel follows at a modest fraction. In meteorites that fell to Earth, the two live together as alloys and in sulfides, their companionship written into metal beads and troilite grains. To peel one partner into the gas while the other stays hidden requires a mechanism that does not simply copy primordial ratios. Something at the surface or within the dust prefers nickel, or something about the pumping, quenching, or geometry favors its visibility. Either way, the spectrum insists that nickel rises where iron barely stirs. Paths toward that outcome begin with the grains. Dust lifted from a small nucleus is a mixture of silicates, organics, salts, and metals. If a fraction of those grains carry nickel compounds that are more volatile, they could give up nickel atoms at lower temperatures. Nickel carbonyl is an example that theorists hold like a delicate vial, a molecule that is volatile at modest warmth, formed when nickel surfaces meet carbon monoxide under the right conditions. If microenvironments in cracks allow carbon monoxide to pool and react, a veneer of such carbonyls could condense on grain surfaces. Sunlight or mild heating would then release nickel atoms through photodissociation, leaving iron behind in sturdier phases that do not surrender so easily. Another route invokes photodesorption from sulfides and organometallic sites. Ultraviolet photons can kick atoms out of lattices, especially from surfaces that have been irradiated into disorder by cosmic rays over long journeys. If nickel sits nearer the skin in certain mixed grains, it could become the easier target. Iron buried deeper would wait for stronger heating that never arrives at large heliocentric distances. In that picture, the spectrum maps a stratigraphy measured in micrometers rather than kilometers. The light is reading crust, not core. A third idea leans on fluorescence. The sun is not a single color. It is a complicated lamp whose spectrum has bright pieces and dark pieces. Nickel transitions that happen to align with bright solar features gain an advantage. Iron transitions that fall into solar troughs struggle. Atomic lifetimes, branching ratios, and the presence of metastable states modify this balance further. If nickel's accessible transitions line up with favorable pumping while iron's do not in the observing band, a modest difference in abundance can be amplified in brightness by physics that cares more about frequency than about intuition. The result would still require nickel to be present in the gas, but it would not require a heroic separation in composition. Whatever the mechanism, the timing carries implications for where in a protoplanetary disk such grains might have formed. Nickel bound into compounds that decouple from iron at relatively low temperatures hints at cold chemistry, either inherited from the natal molecular cloud or assembled in outer disk zones where carbon monoxide and carbon dioxide freeze. There, on the surfaces of tiny grains, reactions assemble unexpected molecules in the quiet between bursts of radiation. The mix then becomes cargo when the grains are built into pebbles and planetesimals. A small body launched into interstellar space keeps that inventory with a fidelity no laboratory on Earth can mimic. To move from poetry to arithmetic, observers convert line intensities into abundances and then into ratios. The nickel to iron ratio in the gas phase, constrained by upper limits on iron lines, tilts high compared to bulk cosmic values. Even if the number is only a bound, the gap between that bound and normality is steep. It pushes models toward asymmetry in release or excitation. It also invites a specific prediction. If the driver is volatile chemistry that favors nickel, then as solar distance decreases and the thermal regime shifts, iron should begin to rise. If the driver is radiative, the ratio may stay skewed regardless of distance, and changes in heliocentric velocity or phase angle could alter line strengths without restoring iron's voice. Monitoring across geometry becomes an experiment staged by the orbit. Nickel atoms, once free, do not survive indefinitely. They are ionized by solar ultraviolet light and swept into the cometary plasma environment where fields can guide them into structures that optical instruments will not follow. The neutral phase is a brief interlude. That brevity helps when interpreting line widths and shifts, because the atoms do not travel far before changing electrical citizenship. The observed lines remain centered and narrow. They tell of release not far from the place of detection, within a few thousand kilometers of the nucleus, where jets and sunlight make their quiet bargains. If nickel can be freed so easily, what else might be? Cobalt, copper, and zinc live near nickel on the periodic table and often share mineral hosts in meteorites and dust. Their lines are more challenging and their atomic constants less favorable, but their presence would either confirm a selective mechanism or show that a broader suite of metals answers the same invitation. Detection of companions would tilt the narrative toward a general surface process. Continued loneliness for nickel would keep the carbonyl hypothesis and similar selective chemistries in play. Each additional line is a small bench in a growing courtroom of evidence. The absence of iron in the gas does not mean iron is absent from the body. It may be abundant but trapped. Dust analyses through polarimetry and scattered light modeling can reveal whether grains show reflective properties consistent with metal inclusions or iron-rich silicates. Mid-infrared features in thermal emission can hint at sulfides, whose presence would satisfy the inventory without appearing in the gas. Combined, those tools would let researchers balance the books. Little iron in the air, much iron in the stones, with nickel choosing both pathways depending on local circumstance. This spectral result reverberates into dynamics. Non-gravitational accelerations depend on where and how gas leaves the surface. If nickel-bearing molecules or photochemical release focus emissions from particular vents, the pattern of thrust on the nucleus becomes more structured. that structure can alter spin in discernible ways. A slow drift in rotation period or a subtle change in light curve amplitude would point toward persistent directional outgassing. Even if nickel itself contributes little momentum compared to main volatiles, its diagnostic value makes it a tracer of the underlying machine. There is a philosophical undertone in watching a quiet metal sing louder than its louder cousin. Nickel shines in the bodies of old coins and in the cores of differentiated worlds. Here, it glows as a thin gas lit by a star, hinting at chemistry that is both fragile and ancient. A traveller carries that chemistry across gulfs, where time eats fine details and spares only the most stubborn structures. The lines seen in the blue-green swath of a spectrograph are enough to sketch a chain of events that begins in dust far from any sun and ends in a telescope on a mountain. Care must be taken with hope. Spectra, this subtle, are vulnerable to calibration sins. Standard stars must be observed, instrument response must be flattened, and atmospheric extinction must be measured rather than assumed. Teams cross-check with independent instruments and schedule repeat nights to ensure stability. They also test analysis pipelines with artificial lines injected into real data, a rehearsal that can expose bias. When the same nickel signal returns under altered settings and with new calibrations, caution relaxes into acceptance. The ultimate reward of this chemistry would be a map, a spatially resolved atlas of nickel brightness around the head, a velocity field measured by minute Doppler shifts, a time series that shows vents turning on and off with rotation, and a parallel set of constraints on other metals. With such a map, the story of release would step from possibility into architecture. Even partial pieces of that map matter. A single slit placed along the sunward fan, shifted by a few arc seconds from night to night, samples a different chord each time and lets reconstruction begin. In the smallest of signals, a large theme emerges. The galaxy builds worlds and then crumbles them under collisions, tides, and chaos. Shards leave, carrying catalogues of bonds and textures that reflect the places where they once slept. Light has the patience to read those catalogues when they drift near a star bright enough to write its spectrum across their skins. Nickel turns out to be one such reader's mark, a note in the margin that refuses to fade. In that note is a reminder that the materials of planets and comets are not only rock and ice and gas, they are also pathways for subtle molecules that form in the shadowed corners. When those molecules let go of a single atom, and that atom catches a solar photon and returns it with a new accent, a biography widens by a page. Images collect in quiet stacks, and a strange geometry keeps repeating. A pale lobe seems to lean toward the sun instead of fleeing it. The classic sketch of a comet would draw the tail away, a banner carried downwind by light and plasma. Here the dust near the head grows a small beard in the sunward direction, a soft wedge that looks like a mistake until too many nights confirm it. In that wedge is a lesson about the stubbornness of heavy grains, the direction of vents, and the ways projection can trick a patient eye. Radiation pressure pushes most dust away from the sun with ease, but the push depends on size and density. Tiny grains, feather light for their area, feel the pressure strongly and race downstream. Large grains carry mass that outvotes their cross-section and behave almost like stones thrown into a river. If a vent launches such grains with even a modest initial speed toward the sun, they keep moving sunward for hours before the constant light persuades them to slow and turn. The result is a sunward fan that stands close to the head, shaped like a shallow triangle or a rounded wedge. Its edge is crisp, where the flow is focused and soft, where overlapping release times blur one day into the next. Models that map dust trajectories illustrate the effect with a simple language. Assign a grain a value that measures the ratio of light pressure to solar gravity. Let that value fall as grains grow, and set initial speeds according to size. Plot the curves for many sizes and many release times, and the image begins to look like the telescope frames. Lines clustered near low ratios bend only gently, lingering near the nucleus and tracing the sunward side before they finally drift into the main tail. Lines with higher ratios sweep away quickly and fill the antisolar direction with haze that loses structure fast. The coexistence of both families draws the peculiar teardrop silhouette many observers notice first. A second sculptor works quietly in the background. The direction and timing of vents matter. If the active region sits near the subsolar point, grains exit with a bias toward the sun at local noon and toward the limb at local morning and evening. Rotation keeps sweeping the vent across day and night, and the head grows a pattern that repeats with the nucleus period. When the cadence of imaging is fine enough, faint streamers appear like ribs within the sunward fan, each rib a brief episode when the vent looked directly into sunlight. The spacing of these ribs remembers the spin, the opening angle remembers the latitude of the source, and their contrast remembers how abruptly the vent switches on as it crosses into dawn. Perspective joins the conspiracy. When Earth crosses the plane of the orbit, a sheet of dust that normally looks like a tail collapses into a line of sight and can project as a narrow feature that appears to point sunward. This illusion is not deception but geometry. Particles ejected gently in the orbital plane form a thin sheet that, when seen edge-on, loses depth and gains brightness. For a span of days, the sheet can seem to contradict the antisolar rule. Careful plotting of the viewing geometry predicts when such plane crossings should produce this effect. A match between prediction and images marks projection as the main artist. A mismatch keeps the case open for genuine sunward emission from heavy grains. Polarimetry adds a sensitive measure to this discussion. The degree of linear polarization of scattered sunlight depends on particle size, shape, and refractive index, and it varies with the angle between sun, dust, and earth. If the sunward fan is dominated by large, compact grains, the polarization curve can differ from the curve measured in the main tail, where small, fluffy aggregates often rule. A lower degree of polarization in the sunward lobe compared to the antisolar side, at the same scattering angle, becomes a quiet fingerprint of hefty grains, launched with enough momentum to ignore radiation pressure for a while. Grains do not leave the nucleus as ideal spheres. Many are fractal aggregates with voids and delicate bridges. Others carry coatings of organics or salts that alter absorption and thermal behavior. A subset may be rich in embedded ices that continue to sublimate as they travel, creating a tiny rocket effect that changes their paths by millimeters per second. Even such minute accelerations add up over thousands of kilometers and can tilt the sunward structure into asymmetry, stronger on one edge where a vent prefers a particular orientation, weaker on the opposite edge where grains fracture or clog. The overall wedge remains, but its internal shading tells a story of grains that keep changing as they drift. Electric fields in the coma can complicate the picture for the finest particles. Solar ultraviolet light charges grains, and currents in the flowing plasma set up fields that guide those with the smallest mass. This guidance can carve filaments in ionized gas, and can also sweep submicron dust into faint rays. Yet the sunward feature that stands out in deep stacks tends to be richer in larger grains, the same grains that pay little attention to fields. The electric forces may embroider the edges with delicate detail, spikes and arrows that flicker with solar wind changes, while the main body of the wedge owes its existence to plain mass and momentum. Spectral color along the sunward fan often shifts subtly. Regions dominated by larger grains can look slightly redder in the optical than regions dominated by finer particles. Laboratory work with analog materials shows that porosity and size alter how light is reflected, absorbing blue more efficiently in some mixtures. When this gradient is measured across the head, it anchors the inference about grain size with a second, independent argument. A gentle red tilt toward the sun and a flatter or bluer tone downwind fit the heavy grain scenario with pleasing coherence. Time makes the fan breathe. As the phase angle changes, forward scattering enhances brightness near the line to the Sunday. The lobe seems to thicken at certain geometries and to retreat at others, even if emission rates remain steady. Observers correct for these angular effects, but the sky is not bound to their corrections. Subtle shifts in the distribution of sizes, or small changes in vent activity, can hide inside the same photometric movements attributed to geometry. Long runs of images, taken with a consistent instrument and cadence, give the best chance to disentangle these effects. They show the fan waxing and waning with a rhythm that combines viewing angle, rotation, and genuine changes in flow. Fragmentation injects a different tempo. Large grains can break as thermal stresses find cracks or as sublimation vents within them reshape their weight-bearing skeletons. Each fracture can produce a momentary spray of smaller pieces that surrender quickly to radiation pressure. Short, curved streamers peel off the sunward wedge like smoke lifted by a gust. These events are small compared to the overall mass budget, yet they are valuable as traces of fragility. Their frequency and shape speak to the grain's internal structure and to the skill of solar heating at finding weaknesses. The sunward feature has practical consequences for measurements that try to resolve the nucleus. A bright wedge close to the core raises the background level near the point source and can bias attempts to set limits on the solid body's size. Analysts compensate by modeling the inner coma as a sum of components: a symmetric envelope, an antisolar tail, and a sunward fan with its own spatial profile. Subtracting this model clarifies the point source and yields tighter size bounds. The quality of those bounds depends directly on how honestly the sunward structure is captured. A lazy model will leave ghosts. A careful one will pull the core out of the fog with no apology needed. There is also a gentle effect on dynamics. Heavy grains that linger close to the head carry momentum that returns to the nucleus through gravity as they arc and settle into the tail. The net thrust on the body from dust emission depends on the direction and speed of this flow. A sunward wedge, weighted by massive grains, can reduce the effective recoil compared to a purely anti-solar spray. That reduction influences subtle non-gravitational accelerations, inferred from precise astrometry. In the ledger of forces, dust geometry matters almost as much as gas. What does a sunward lobe mean at the level of origin? It suggests vents able to hurl large particles with discipline rather than with chaos. It suggests cohesive clumps within the near-surface layers, aggregates that survive launch and only later fall apart. It suggests a crust that opens in mouths large enough to pass pebbles, not only pores that sift powder. Those traits arise naturally in materials that have been sintered by radiation and microheating in long, hard winters between stars, then cracked by gentle thermal tides when sunlight arrives. The image on a screen, a little fan leaning toward the sun, becomes a portrait of that near-surface world. The eye learns quickly once it knows what to look for. Subsequent frames become easier to read. The wedge appears on nights with steady seeing, and fades on nights when noise smothers low-contrast features. The inner edge rides along a line that marks the solar direction, with a tightness that feels almost architectural. The outer edge dissolves into the wider coma, where light pressure finally wins. Beauty and mechanics share the same small space. A viewer might only see a delicate asymmetry and feel the calm of small physics at work. A practitioner sees a book of numbers written in that calm and begins to turn pages. The path unfolds as a clean geometry drawn against the ecliptic, a visiting curve that slips through the inner system without touching anything it could bruise. Planetary orbits stand like chalk circles on a schoolyard. The traveller traces a line that dips inward just far enough to taste stronger light and then climbs away again. The mist distances are generous. There is no crossing of a planet's body, no grazing of a moon, no whisper of collision mechanics. Gravity bends the course, but the bend is modest because the inbound speed carries more energy than the sun can seize. The encounter is a skim, not a plunge. At the heart of the dance sits a single point of closest solar approach. The word for that intimacy is perihelion. Nothing magical happens there that physics has not already promised. Yet the moment deserves attention. Solar flux reaches its peak, setting the temperature of surface layers and dictating what ices can live and what must flee. Gas production rises in step with warmth, and dust joins with a stubborn sense of timing that belongs to grains rather than clockwork. The shape of the orbit sets how long this high state lasts. A brisk hyperbolic arc spends little time near the sunday. The spike is sharp. Observers know to aim their best instruments at that narrow window, because the object will not wait politely for a schedule to catch up. Safety for Earth and the other planets is read from a measure with an elegant name, the minimum orbit intersection distance. It is the clearance between the visiting track and each planet's path, adjusted for where the bodies actually are during the pass. For this traveller, the clearances are spacious. Even gravitational focusing at high speed cannot pull the line down to a dangerous meeting. The reassuring arithmetic hides a curious grace. A fast visitor is largely immune to being captured or diverted. The same speed that makes chasing a challenge also makes hazard unlikely. Inclination colours the scene with perspective. The orbit does not lie flat on the ecliptic like a lazy coin. It arrives at an angle that carries the object above or below the planetary plane before its turn toward the Sun and again as it departs. The two crossings of the ecliptic are the nodes, and they schedule which hemisphere enjoys the easiest vantage. If the incoming node lies in southern skies, southern observatories gain the first long looks. If the outgoing node favours northern latitudes, the baton passes as the object leaves. This choreography is not an accident of fate. It is the simple result of geometry, but it feels like generosity shared across the globe. Viewing is ruled not only by where, but by how far from the Sun the object sits in the evening or morning sky. Solar elongation is the name of that angle between target and star as seen from Earth. When that angle shrinks, glare swallows, faint structure, and even bright comae become ghosts. When the angle widens, the sky darkens and the visitor steps forward. A hyperbolic passer lunges through values of elongation quickly. The schedule of opportunity is a brief fan of days when the angle is kind. The phase angle adds a dash of forward scattering for extra brightness, and weather has the manners to cooperate. Teams plan for those handfuls of nights the way sailors plan for tides. Motion on the sky accelerates as distance from Earth decreases, and as the true anomaly rushes through perihelion. Apparent rates can jump from slow strolls that sit comfortably inside the tracking of a sidereal mount to fast cuts that streak across detectors in minutes if the telescope does not follow. The practical effect is plain. Shorter exposures are required to keep the head sharp. Stacks must account for motion to avoid smearing the tail into indecision. The very speed that proves the interstellar nature becomes a practical variable on a control panel. Thermal consequences ride on distance to the Sun with the clear discipline of the inverse square law. Double the proximity and the energy on each square meter of surface jumps by 4. Sublimation that barely breathed at the edge begins to talk. Fractures evolve as stresses steepen, and vents shift personality as shade and sun move across the broken skin. A nucleus that never meets enough warmth for water to dominate can still erupt in its own language of more volatile molecules. Perihelion concentrates that story into a short season, a crescendo that reveals what the machine inside the crust can accomplish when it is fed. The plasma environment transforms in the inner regions. Solar wind density and magnetic structure strengthen with proximity, building a playground where ions and electrons sketch boundaries. Ion tails stretch with a delicate sense of purpose. Bow shocks and contact surfaces appear where charged particles are deflected. Even a modest coma can carve a small territory where the solar wind reconsiders its path. Measurements of those boundaries translate into rates of gas escape and the strength of the interaction with sunlight. The map of these invisible forms rides on the same trajectory that keeps the dust in motion, a second layer of the same passage. Instruments in space add their unique advantages during the skim. Without atmospheric absorption, they can watch wavelengths that ground-based mirrors cannot see. Without seeing blur, they can bring the inner coma into a sharpness that makes structure obvious. The complication is scheduling. Rapid changes in position and brightness must be matched by cues that can turn with agility. The target does not linger in regions of sky where a spacecraft has long booked programs. When everything aligns, images arrive that peel back the inner 1,000 kilometers, as if a veil had been lifted. Jets appear as thin fans. The inner edge of the tail resolves into braided filaments, and the brightness profile near the core turns into a quantitative line that points towards size and albedo. For those who trace gravitational dynamics, the skim is a clean experiment in deflection. Inbound and outbound asymptotes define an angle that depends on impact parameter and excess speed. The number is small by human taste, but it is real. The sun turns a straight line into a near straight line that has been politely nudged. That nudge has consequences for the outbound direction on the celestial sphere. Radio arrays and optical astrometry combine to write this angle with precision that lets small forces announce themselves. If outgassing on one face of the nucleus adds a whisper of thrust, the final direction reveals it. Even without close planetary encounters, dust in the orbit that the traveller crosses can brush the coma and tail. The zodiacal cloud is not uniform. Denser lanes associated with old comet streams sweep the ecliptic like translucent rivers. When a fast interstellar body slices through such a lane, relative velocities are high but densities remain thin. The effect is subtle and probably decorative rather than disruptive. A few fragments may collide with grains and splinter them into smaller pieces, briefly brightening certain sectors of the tail. Polarization maps can pick up such changes as a shift in the curve that relates scattered light to angle. Illumination conditions change color as the object rounds the sunday. Morning apparitions can make an object, a sculpture in the pre-dawn blue where the atmosphere is quiet, but the clock is cruel. Evening apparitions put the same head and tail against a darker vault where airglow and city light must be tamed. The choice between those two modes is not made by observers. It is set by the geometry of the pass. Many find themselves awake on both sides of midnight, reading the sky in the same small hours that once belonged to sailors and radio operators. No planet is threatened, yet satellites and dust-sensitive instruments benefit from a simple reckoning of risk. A hyperbolic visitor carries debris that it sheds, but the densities are nowhere near the levels required to endanger spacecraft, except at the instrument aperture level, where even a single grain would be unwelcome. Operators note the time and sector of sky, angle instruments away if prudence asks, and carry on. The sky hosts a transient drama, not a storm. Perihelion itself, when it arrives, is quiet in a way that contradicts the romance of the word. The object does not flare like a match. It does not crack in half with theatrical timing. It obeys temperatures and pressures that can be written calmly on paper. Dust escapes according to energy budgets and pore sizes. Gas lines climb in measured increments that spectrographs record without fuss. The imagination knows that poetry lives here, yet the instruments see a system that behaves. Satisfaction comes from that steadiness. In the middle of a dramatic curve carved through the solar system, the physics remains a set of patient rules. Departure begins immediately because nothing holds the visitor beyond the brief handshake of gravity. The outbound path mirrors the inbound path in distance and time, with only minor edits imposed by activity. Sky rates slacken, elongation changes character, and opportunities for deep imaging return after a glare-filled pause. The object will still be bright enough for the largest mirrors for a modest while, and then it will cross a threshold where only the patient can follow. The passage has been safe for Earth from the first calculation to the last sighting. Safe and generous with information for those who learned its timetable. Two names sit like bookends on a new shelf of knowledge. The first is a shard that crossed the inner light with a shape that defied easy imagination, faint, fast, and quiet enough to leave chemistry largely hidden, while its motion hinted at faint forces at work. The second is a classic wanderer by appearance, throwing a bright coma and a long tail, its behavior closer to the comets familiar to planetary science, yet tinted by a chemistry that did not quite match the local recipe. Between those bookends, a third volume now slides into place, and the shelf stops looking like a curiosity and begins to resemble a small library. A field that once had astonishment and then comparison finally gains the first outlines of pattern. A single visitor can be an anecdote. Two can be an argument about difference. Three begin to write statistics in pencil. Rates, biases, and categories step out of speculation and into cautious arithmetic. The pipeline that finds such bodies has grown steadier with each discovery, and the sky, indifferent to our readiness, keeps offering tests. The new object widens the span of properties that interstellar debris can display, filling in a triangle of possibilities that stretches from nearly inert slabs to vigorous comae. That triangle is not a complete map, but it shows that other suns throw off more than one kind of fragment when they rearrange themselves. Size and brightness paint the first comparative portrait. The earliest traveller was small by any planetary standard, probably closer to a building than a mountain, its shape inferred from a light curve that whispered extremes. The second carried a solid heart nearer to a kilometre across, revealed through the fog of its own gas and dust by methods that track the fade of light in time and space. The newcomer, measured through the veil of an active envelope, sits within an upper limit that allows a compact worldlet, a modest object by comet standards, but rich enough in surface floors to ventilate under sunlight. The trio shows that ejection does not prefer a single scale. Fast shards can be small and nearly bare, and they can also be sizable and loaded with volatiles. Motion writes the second portrait. Each arrival came in with a speed that refused adoption, yet the details differ in temperament. One cuts so quickly through the inner regions that the best instruments met it only after it had already turned for the dark. Another announced itself with activity at greater distances, allowing a long runway of observation. The newest follows a path that grants a safe skim and a short crescendo near closest approach. These differences are not accidents. They spring from the geometry of the hyperbola, the angle to the ecliptic, and the timings that set morning or evening apparitions on Earth. Together they teach how configuration filters what we can know. Fast, faint, and nearly naked is hard to characterize. Slow enough and active enough is the generous teacher. Composition hints add the third portrait. One left puzzles about faint accelerations without obvious gas, encouraging ideas about volatiles that escape invisibly, or about dust behaving in unfamiliar ways. One displayed carbon-bearing molecules in healthy abundance, closer to the outer reservoir behavior that comet books describe. The new arrival favors volatiles that wake early, painting its first days with lines in the infrared that speak of colder chemistry rising ahead of water. This spread of behavior makes a simple lesson. If other disks and other winters bake and shelter their small bodies differently, the gallery near the sun will inherit that variety. Some cores will be crusted and stingy, others ready to boil out long before warmth grows friendly, and a few will appear almost quiet while still feeling faint pushes that shift their paths. The trio also tests origin stories. Planetary systems eject debris by several routes. Giant planets stir planetesimals and fling them outward like slings. Binary stars trade energy with small bodies and make exile cheap. Densely packed newborn clusters shuffle orbits while gas still lingers, and ice-rich relics are thrown into interstellar night. The first two arrivals could each be claimed by different mechanisms. One perhaps a fragment from deep inside a young system that suffered collisions or thermal stripping, the other a more typical icy remnant of a cold outskirts. The third fits easily within the family of bodies that formed beyond a water-snow line, but kept access to molecules that prefer colder homes, suggesting a birthplace in the middle country of a disk, where a volatile like carbon dioxide freezes while water remains asleep beneath a processed rind. The point is not to fix a single map, but to display a menu of kitchens where such objects are cooked. Detection bias becomes an unromantic but crucial teacher. A small, inactive parser must come very close to be seen by present surveys, while a dusty object announces itself from farther away and grants time for triangulation. The first interstellar sighting was surprise at close range. The second was a comet noticed early because its own breath betrayed it. The third shows the efficiency of modern cadence at spotting a faint inbound ember before it reaches its brightest season. This bias explains why the first catalogue entries can look skewed. Easy quarry arrives first, and only a wider net will reveal the true distribution of types and sizes that drift between stars. Dynamics and chemistry cross paths in the trio in ways that sharpen method. Faint non-gravitational accelerations in a nearly inert body force theorists to revisit the microphysics of outgassing, the shapes of aggregates, and the way surfaces release energy. Strong, obvious activity in a classic comet gives clean gas lines and dust tails that can be modelled with trusted tools. A new object that breathes in a way that favours early waking volatiles pushes instruments to wavelengths where space-based observatories shine. Across these styles, a single unifying practice emerges. Precision astrometry paired with spectral patience will always be the anchor. When speed and geometry allow only a short campaign, that pair still yields the decisive clues. Shape becomes an unquiet subplot. A high-amplitude light curve implies a long, thin form or a flat, wide one, each with challenging stability under torques. A coma hiding a nucleus makes such inference difficult, yet the character of jets and the modulation of brightness across rotation can hint at contours. In one case, the debate over cigar or discus opened larger questions about how brittle solids break, how thermal processing changes aspect ratios, and how gentle thrusts spin or settle tumbling. In another case, the more ordinary nucleus shape played second to the chemistry of the coma. The newcomer will carve its own niche in this debate as rotation measurements refine. Uneven vents, sunlit fans, and small changes in light can map shape cautiously even when rock cannot be seen. A single theme becomes visible when the three are placed on a single canvas. Planet formation is messy, and the galaxy is full of leftovers. Disks build worlds by accretion, then prune their edges with gravity and heat, exporting what does not fit. The inventory of refugees contains rocks scraped clean, ices layered with processed skins, and composites that still carry the fragile molecules forged on grains. Every arrival near the sun is a chance to weigh how common each ingredient is. Even when the answers come wrapped in ambiguity, the conversation narrows. Volatile dominance at cold distances means some disks front-load carbon-bearing ices. A faint push without visible gas means microvents and exotic carriers are at least plausible. A textbook comet from afar says that the galaxy does not withhold the familiar either. Anticipation follows naturally. If three objects can find their way into a single human lifetime of instruments, then a dozen can follow once the largest survey cameras begin their nightly harvest. With more arrivals, the stick figures of trend will fill with muscle. Size distributions will gain slopes and breaks instead of guesses. Chemistry will split into subfamilies. Kinematics will trace the motions of stellar neighborhoods, testing whether most fragments ride with the thin disk, drift with older populations, or carry memories of clusters long dissolved. The new object, slotted beside its two elders, is the key that turns speculation into program. The broader meaning reaches beyond catalogues. A small stone or ice globule that crosses a star field pulls imagination in its wake. It reminds the observer that other habitable zones glow somewhere behind the sky, that other storms fall on other worlds, and that debris carries stories even when it cannot be returned to a lab. These arrivals are not messages in the deliberate sense, yet they are messages in the physical sense, samplers of a chemical and dynamical language spoken across the spiral arms. The first word startled, the second clarified, the third invites grammar. The shelf will grow. When it does, historians of this subject will look back at the season when there were only three and see an inflection point. Before that season, interstellar planetesimals were thought experiments and improbable footnotes. After it, they became routine topics in seminars, proposal titles, and student theses. The trio is not the whole story. It is the first stable base for a field that now stands upright. The promise is simple enough to recite. With each visitor, the invisible architecture of other systems becomes less invisible. With each spectrum, the list of possible origins shrinks. With each track on the sky, the galaxy feels a little more connected, as if the space between suns were not empty but threaded with quiet traffic. Speed in space is a kind of memory. A body that crosses the inner light at tens of kilometers per second carries a ledger of past encounters engraved in its motion. The number that matters most is the velocity it would still hold if the sun's pull faded to zero, a surplus that marks a traveller as unbound. That surplus is not born near here. It is the sum of an ejection from a distant nursery, and the drift of that nursery through the galaxy. Giant planets in young systems can fling small worlds outward with a single close pass. Binary stars can trade energy with even greater efficiency. Add the stellar motion that all suns share as they circle the galactic center, and a range of speeds appears that easily outpaces any hope of capture. The visitor's path bends, but the arrow keeps its tip. Kinematics turns this poetry into tools. The inbound velocity vector, expressed in the quiet arithmetic of 3 coordinates, fixes a line through space that points toward a patch of sky where the object seemed to come from. That patch is not a birthplace, only a direction shaped by time and gravity, yet it acts like a compass. Compare that vector to the motion of nearby stellar streams and the thin and thick components of the Milky Way, and the speed begins to sound like an accent. Membership in no family can be assigned with certainty, but probabilities grow from such comparisons. A fast approach aligned with common disk motions implies a long cruise between ordinary stars. A stranger angle or a higher excess speed tempts thoughts of an origin in systems that were stirred more violently, or of scattering long ago when a parent star wandered through a crowded region. The same vector writes the length of the stage on which instruments must perform. Apparent motion on the sky accelerates as Earth and the visitor change their geometry. It can be gentle when far and brisk when near, a transition that divides the useful nights into 2 styles. Early work favours deep exposures and stacks that follow the moving target across the stars. Later work prefers short frames and precise tracking that keep the head sharp while the background becomes streaks. The velocity also governs how long fresh sunlight has to explore the surface. A slow comet lingers near its warmest hours. A rapid interstellar passer grants a brief season of peak heating and then is gone. Spin is the second half of this portrait. Rotation is a clock hidden inside the coma, and it shows itself through small changes in brightness as vents turn toward the sun, as jets sweep across the line of sight, and as shapes with unequal faces reflect light unevenly. Extracting that clock from a soft halo is careful work. Photometry within a fixed inner aperture must be corrected for seeing so that atmospheric blur does not mimic real change. Background stars must be masked from stacks so that their trails do not contaminate the rhythm. The result is a time series that can be sifted with period searches designed for uneven sampling, since nights and weather cut gaps into any earthly campaign. Even a modest light curve teaches. A repeating pattern with a single dominant period suggests a principal axis rotation. 2 nearly equal peaks hint at a shape with pronounced elongation, since one long face and its opposite reflect more light than the narrow profile. A pattern that refuses to settle on a single period suggests a more complicated state. Non-principal axis rotation, the slow tumble of a body that has been jolted by an impact or spun by uneven thrust, will smear the signal into a beat pattern. Such tumbling is common among small bodies that have not been damped by internal friction. The timescale for damping depends on size, rigidity, and the quality factor that measures how efficiently the interior turns deformation into heat. For a compact kilometre-class nucleus, damping can take far longer than a human lifetime. For a loose aggregate, it can be quicker, but still not swift. Rotation also governs safety for the body itself. There exists a critical period below which a strengthless rubble pile would fly apart. That threshold depends on bulk density. Higher density allows faster spin without failure. Lower density raises the risk. If the period drops near that limit, cohesion in the near surface layers, or monolithic strength in a larger fraction of the nucleus must carry the excess. The light curve amplitude adds a second constraint, since large swings imply elongated shapes whose tips feel stronger centrifugal stresses. A measured period that sits safely above the limit argues for a comfortable margin. A period closer to danger invites speculation about internal ties that resist breakup. Outgassing writes on the spin in quiet increments. gas that leaves from a vent not at the exact center of mass exerts a torque. If the vent favors one hemisphere, the torque can persist across many rotations and act like a tiny engine. The sign and magnitude of this spin change depend on the map of active areas and on the seasonal march of the subsolar point. Some bodies spin up under such torques, others slow down. In either case, long runs of photometry can reveal a drift in period that is too small to be seen in a single night, but obvious across weeks. Spectroscopy can even tie changes in gas emission to phases of the light curve, confirming that the clock and the chemistry share a common engine. There is a third actor in the spin drama. Sunlight itself can alter rotation through recoil from reflected and thermally re-emitted photons. This effect is delicate and cumulative. It depends on shape, on surface texture, and on how heat flows through the skin. It can drive spin states on asteroid timescales measured in years to millennia. In a short solar passage, the effect is small, yet not exactly zero. A body that already sits near a threshold can feel even a slight nudge. The main stage for meaningful change remains gas torque, but the photon push is a note worth holding in the background. Spectral lines can join photometry to probe the rotation more directly. If a jet is narrow and stable, the velocity profile of gas along a slit aligned with that feature will change as the vent turns. Blue shifts give way to red shifts as the flow swings across the observer's line of sight. Periodic reversals that match the photometric clock would confirm a rotation solution and fix the pole orientation more tightly. In dust, the same effect can be seen as fans that brighten and fade at positions that drift with the spin. High cadence imaging near peak brightness is the canvas on which such subtle choreography becomes clear. The spin is not immune to history. Ejection from a parent system can impart a final kick that sets a body tumbling. Collisions in the interstellar night are vanishingly rare. So whatever rotation state the object carried away from its origin will survive largely unchanged across the gulf. Radiation and micrometeoroids will sand the surface, but without strong torques, the interior clock keeps its inherited tempo. That persistence is valuable. It makes rotation a fossil of the early violence that set the fragment free. A fast spin hints at tight encounters with large planets, or at catastrophic breakage that left shards with high angular momentum. A slow turn whispers of gentler birth. Gravitation adds one more brushstroke. During the brief time near the Sun, tidal forces act across the nucleus. The difference in pull between the near and far sides is tiny for a small body at safe distances, yet it is real. In aggregate, it can modify the tumbling of a loose aggregate if the structure is near certain resonant states. The effect is not expected to dominate, but careful modeling can place limits on what the encounter might change. Observers test these ideas by looking for subtle shifts in light curve shape before and after the warmest days, recognizing that gas torques will likely speak louder than tides. A complete solution couples all these clues. The period and amplitude approximate the elongation. The presence or absence of secondary frequencies points to tumbling or to simple spin. The drift of period with time quantifies torques. The phase of spectral or morphological changes anchors the pole. With those pieces, density becomes the next target. If an independent size emerges from thermal measurements or sharp imaging, then the threshold for rotational breakup can be compared to reality. That comparison turns into a bound on bulk density and therefore on the mix of ice and rock inside. Speed and spin finally touch in a single insight. The velocity through the solar system is a relic of gravity writ large. The rotation is a relic of forces writ small. Together they describe the same life, one chapter in a crowded young system where giants rolled dice with planetesimals, and one chapter in an old, thin dark where nothing much happened except the long patience of travel. Instruments can read both chapters at once. A track of positions on the sky yields the vector that will never close. A track of brightness in time yields the rhythm that will not easily change. The body moves like an arrow and turns like a clock, and both arrow and clock are true. Color carries quiet information, and dust is the page on which it is written. When sunlight strikes a veil of grains, the reflected spectrum tilts with a slope that observers measure against the sun itself. Normalize the continuum at a green anchor, then watch the reflectance rise toward the red. The climb is gentle, a few to a dozen% per 100 nanometers in many komae, enough to be obvious on a plot and subtle to the eye. That tilt is not a decoration. It is a fingerprint of grain size, structure, and skin chemistry etched by cold time. Photometry in broad filters gives the first clues. Compare magnitudes in bands that avoid the bright gas features and translate those differences into a reflectance slope. The result is redder than solar, but not extreme. This is the classic language of irradiated surfaces and porous aggregates, grains that have lived where cosmic rays scratch bonds and ultraviolet light carves new ones. Fine particles tend to backscatter blue light less efficiently than red when their surfaces carry complex organics, so the continuum leans toward longer wavelengths. The same colors appear across many cold populations, from distant asteroids to outer system comets, a family resemblance drawn by the long patience of space weathering. Narrowband filters refine the message by dodging emission lines that would confuse the continuum. Standard windows near 443, 525, and 684 nanometers let dust speak without the voices of CN or C2 singing over it. With those windows, a clean slope emerges that can be compared night to night and region to region within the coma. A consistent red tilt across the inner few thousand kilometers means the source regions are feeding the same kind of grains into the flow. A soft gradient that cools slightly toward the tail hints at fragmentation, where large clumps break and shed finer pieces that scatter light differently than their parents. Scattering physics explains why size matters. Submicron grains sit in a regime where wavelength and particle dimensions compete. Resonances and interference change how light is redirected, and tiny shifts in porosity or coating thickness can alter the slope with surprising leverage. Micron-sized grains move into a smoother, quasi-geometric behavior, bright under forward scattering, and less sensitive to small changes in skin chemistry. The color that emerges from a mixed cloud is a weighted average of these behaviors. A dominance of larger, compact particles pushes the continuum to a calmer red. A heavy share of very fine, fluffy aggregates tilts the slope more steeply and can introduce curvature that a straight-line fit struggles to hide. Polarimetry adds a second dimension to the same question. The plane of polarization rotates and strengthens according to angle and grain character. At moderate phase angles, komae rich in porous, radiation-processed particles show a higher degree of linear polarization, with a wavelength dependence that usually grows toward the red. Map that polarization across the head and tail, and regions that are redder in color often show stronger polarization, a partnership that points to similar underlying textures. Anomalies become valuable. A blueward patch with weak polarization flags either an intrusion of gas or a pocket of unusually fine dust born from local fragmentation. Phase itself is not an innocent bystander. As the angle between sun, dust, and earth changes, shadows within porous grains hide and reveal themselves. Shadow hiding and coherent backscatter modify the continuum in ways that mimic a change in color. The result is called phase reddening. Careful teams correct for it with empirical laws drawn from many comets, but each body brings its own adjustment. When the true color slope remains stable after correction while brightness varies with angle, confidence grows that real grain properties, rather than viewing geometry, carry the story. The near-infrared extends the canvas. Between 1 and 2 microns, the reflectance often flattens, a sign that the organic mantles responsible for optical reddening absorb less efficiently at longer wavelengths. Beyond 2 microns, the thermal glow of warm grains begins to rise and partially fills the continuum with heat, especially near closest solar approach. Decomposing reflected and emitted light requires models of temperature and size distribution. When that separation is honest, the residual reflectance keeps telling the same tale. moderately red dust, consistent with macromolecular organics and irradiated ices, with a hint of neutralization in the infrared, where absorption features smooth. Laboratory analogues pull these ideas toward matter one can touch. Ices mixed with methane, carbon monoxide, nitrogen, and carbon dioxide, irradiated at low temperatures, darken and redden as complex chains form. Thin films of tholin-like materials spread across mineral grains create the same gentle tilt measured at telescopes. Heat treatments show that modest warming can relax the red slope as volatile residues reorganize or escape. These experiments do not recreate the exact journey of any single traveler, but they sketch a map of possibilities. A measured slope falls on that map in a region marked by long exposure to radiation and only brief episodes of heating, consistent with grains lifted from a crust that has seen many winters and few fires. Color is not just a property of the dust, it is also a tracer of motion. Synchrones and syndines that model the release time and size of particles can be overlaid on color maps to decode traffic within the coma. Sunward fans, rich in larger grains, often carry slightly redder tones. Antisolar filaments that pull fine particles can look less red. Cross-sections through those features, sampled at high cadence, can watch the color of a given parcel evolve as grains, fracture, sublimate, and spin, a slow drift toward neutrality, with distance from the head signals real change in the particles rather than a changing mix swept up by viewing geometry. Measurements of AF rho across multiple filters tie dust production to color. If AF rho rises more steeply in red bands than in blue, the outflow favors particles that scatter long wavelengths efficiently, which usually means larger sizes or thicker organic coatings. If AF rho is flat with wavelength, the emission is either grain size balanced or dominated by neutral, perhaps fresher fragments. Translate those behaviors into mass loss rates, and the arithmetic still carries the color along, because optical efficiency changes the conversion between photons and kilograms. Models that ignore color risk, misjudging how much dust is leaving and what forces that dust can exert back on the source. The nucleus hides, yet color near the very center can hint at its face. Subtract a point spread function constructed from field stars and examine the residual within the smallest resolvable aperture. A slightly redder core compared to the surrounding coma suggests that large, older grains do not travel far before sunlight, and radiation pressure begin to sort them. A slightly bluer core hints at fresh fragmentation near the vents, with fine shards paling the inner few hundred kilometers before they are blown into the tail. Either outcome is a map of mechanics drawn in color rather than in shape. Gas must be kept honest in this account. Blue features from emissions can masquerade as a change in dust color if filters are not chosen with care. Narrowband systems avoid the worst traps, and spectra can confirm that the continuum is indeed dust-dominated. When gas lines do intrude, their subtraction reveals a dust slope that often returns to the same red value as before. This consistency argues that the continuum is not a momentary accident, but a durable property of the grains themselves. Beneath the optics lies the mineral. Silicates with iron inclusions, sulfides, and salts each carry refractive indices that alter how red the spectrum appears once coated with organics. Mixtures with higher metal content can mute color, while fluffy, silicate aggregates with thin organic skins push it redder. If thermal emission imaging supplies a temperature and an effective size, those properties can be coupled to color to infer composition families. The result is not a unique formula, but it narrows the choices. It points toward porous, low-density grains with complex surfaces, rather than dense metallic shards or pure ices stripped of skin. Time enriches this palette. As the object moves away from the sun, the red slope can relax if fragmenting grains shed their coatings, or if fresh, neutral fragments dominate the flow. As it moves inward, the slope can steepen if gentle heating mobilizes organics that migrate to surfaces before being lost. Track these changes, and the color becomes a thermometer and a clock, measuring not temperature directly, but the consequences of temperature married to structure. Color also repeats across scales. The same red tilt appears in faint trails of dust that arch far behind the main tail, relics of earlier days of emission. It appears in the diffuse glow of a broad halo that surrounds the head, built from grains so large that radiation pressure barely moves them. It appears, softened, in the sunward wedge where heavy particles push against the flood of light. A single slope, written in many places, becomes a chorus rather than a solo, and that chorus speaks of a single population delivered by vents that do not change their minds quickly. The optical continuum finally becomes a mood as much as a metric. To an untrained eye, the coma looks grey. To a calibrated instrument, it leans into rust and honey, a quiet warmth that is not heat but heritage. That warmth is the residue of chemistry that thrived in cold, a skin written by radiation that rewrote bonds for ages. Each photon scattered back to Earth carries that biography in its color. Each image taken through patient filters adds a sentence to that biography. The dust is not merely an accessory to the gas. It is the archive that preserves how small things survive long journeys, and it speaks in shades that instruments are learning to translate with care. Astronomers begin with a simple act. They extend the path backward until gravity grows thin. A curve through the inner system becomes a straight intent at the edge. From that straight line, they read a radiant in the sky, the point from which the traveller seems to arrive. Star charts label that quarter of heaven with names carried from deserts and rivers. Constellation lines frame a region rich with distant suns, and the radiant falls among them like a pin pressed through velvet. The direction is a quiet arrow. It names a bearing, not a birthplace. The method is clean in outline. Take positions and velocities measured over many nights. Fit a trajectory that respects the pulls of the planets and the small corrections that keep arithmetic honest. Unspool that motion until the sun's grip fades to the background of interstellar tides. At that boundary, the object is described by a vector, a speed, and a direction that carry the memory of where it was going before it met this star. The speed is the surplus that the sun could not take. The direction is the sky coordinate that instruments can plot on a map. A second transformation replaces the local yardstick with a galactic one. The solar system is not at rest. It drifts through the Milky Way with its own three-dimensional motion. Subtract that drift, so that the visitor's path is measured against what astronomers call the local standard of rest, the average flow of nearby stars. The components of motion in the galactic frame take familiar letters. One points toward the galactic center, one follows the spin of the disk, one lifts toward the north of the galactic plane. In that frame, the radiant becomes a statement about how the traveller moves relative to the neighborhood of suns rather than relative to this single sun. Even before any deeper inference, the geometry teaches restraint. A radiant near Sagittarius means that on arrival, the object aligned with a region where the Milky Way draws a bright river across the sky. It does not mean origin at the center of the galaxy. The sky is a dome that flattens depth into pattern. Lines of travel that begin far above or below the plane can project into the same constellation. In a universe where stars and their debris follow their own long ellipses around the center, alignment is easy to earn and meaning is hard. Uncertainty sits in the fine print. A small error in astrometry becomes a small error in velocity. Run backward across millions of kilometers and the difference is tiny. Run backward across light years and the same difference becomes a wide cone. Planetary perturbations complicate the story further. Even a modest cometary thrust can alter the outbound asymptote by a trace that matters when traced into the past. Analysts cope with this by producing families of clones within the uncertainties and following them backward as a cloud. The result is a smeared ribbon of possibility that crosses constellations rather than a pinprick on one star. Time also erases signatures. Interstellar space is patient but not empty. Radiation darkens surfaces. Micrometeoroids, sand grains. The encounter histories that would act like serial numbers are worn thin. Only the vector persists with fidelity, and even that vector remembers only the last leg of the journey. Long ago, a different vector carried the body out of the system that birthed it. Stellar motion has since bent that old direction slowly as the parent star moved in its own orbit. The arrow that telescopes read today is therefore a palimpsest. It shows where the traveller was headed, not where it began. Still, the vector is useful. It lets astronomers ask which stars were nearby along that line in the recent past. Catalogues of stellar positions and velocities provide a way to rewind the motions of many suns. For each candidate, the calculation is simple in spirit and careful in execution. Propagate the motion of the star and the motion of the traveller in a smooth approximation to the galaxy's potential, and look for close approaches. The goal is not a launch pad mapped to a kilometre. The goal is to find whether any known star passed within a few light years at a time compatible with ejection by planets or a stellar companion. The answer to that search is usually modest. Space is big even within the local spiral arm. Close crossings of a specific interstellar fragment and a known star are rare. A handful of candidates may brush within a few parsecs over a few million years. Each approach is tested for plausibility by considering the age of the star, the presence of giant planets if known, the likelihood that such a system would be ejecting planetesimals at that epoch, and the energy required to reach the measured speed. Most candidates fall away under these tests. What remains are possibilities, not identifications. Bias lies in the shadows of every inference. Survey telescopes search in strips of sky that shift with season and weather. They avoid the sun's glare and favour declinations that match their latitudes. Objects are easier to discover if they approach from regions where the surveys see deeply and often. Radiants therefore cluster not only because of galactic dynamics, but because of human scheduling. A concentration near a given constellation can be a property of opportunity rather than a property of the universe. Correcting for that bias requires models of survey cadence and depth folded into the changing brightness of an object that wakes as it warms. The idea of gravitational focusing offers another quiet caution. The sun's gravity slightly increases the flux of interstellar objects that approach from certain angles by bending their paths inward. The effect is gentle compared to stellar motions, but across large populations it can shape radiant maps. A cluster of directions on the sky can reflect that light touch, not a convoy dispatched from one corner of the galaxy. Models that include this focusing predict a subtle enhancement near the direction of the sun's motion through the local stars, a headwind effect analogous to raindrops striking a moving car. Comparing the measured radiant to that expectation tests whether the visitor simply rode the headwind or arrived from a more unusual lane. On the smallest scales, the radiant influences tactics at the telescope. Its position sets which hemisphere can follow the object for long nights, and which mountains carry the best sight lines before dawn or after dusk. It sets the altitude at culmination and how much air the light must cross. It sets the sequence of fields that observatories can assign without colliding with other programs. In this way, a galactic vector becomes a local schedule, and a theme written across the Milky Way becomes a plan pinned to a corkboard in a control room. Speculation follows where evidence allows. If the line of flight aligns broadly with the rotation of the galactic disk, that harmony hints that the traveller has been part of the settled flow for a long time. If the motion cuts strongly against the stream, more energetic beginnings are suggested, perhaps ejection during the unruly youth of a system born in a dense cluster. If the speed above the local standard is high, that extra energy must be explained by a hard kick in the birth system, or by inherited motion from an already unusual star. Each of these interpretations remains a sketch until more members of the interstellar family are measured well enough for patterns to be drawn with confidence. The material inside the traveller does not announce a postal code. Carbon dioxide rising early, dust with red slopes, metals that resist or assist escape all speak of temperature and chemistry in a young disk. None of them point to a single star on the map. The radiant and the speed add only a compass bearing and a pace. Together they cut the list of possible cradles from infinity to a class of plausible neighbourhoods. That pairing is still a victory. A small body with no language but physics has told a story that narrows where and how it might have been made. There is quiet pleasure in translating a bright smear on a detector into a direction among the constellations. The eye can look where the arrow points and see star clouds like beaten gold around darkness cut by lanes of dust. Somewhere behind that richness, far beyond any single luminous thread, a modest worldlet once orbited a star and felt a disruption that unlatched it from home. The mathematics of radiant and speed cannot restore the ancient sky that body once knew. It can only place a fingertip on the present sky and say, with measured certainty, it came along this line. Instruments fold up after a night spent on that line, and the plots that show vectors and cones of uncertainty find their place among other records. The arrow drawn towards Sagittarius fades with the season. Winter and summer trade places. New candidates appear in other quarters, yet the act remains steady, trace back to the edge, transform to the galactic frame, compare to the drift of nearby suns. Accept that a direction is sometimes the only memory that survives. In that acceptance lives the art of reading motion as biography, not because it names a village, but because it reveals how a life crossed the dark. Size hides in light like a whisper in music. The solid heart at the center of a bright coma refuses to stand alone on any detector, choosing instead to blur into the dust and gas it exhales. To measure that heart, astronomers begin by building a model of everything that is not the nucleus. They map the glow around the core, find how quickly it fades with distance, and fit a point spread function drawn from field stars to represent what a true point would look like. Subtract the modelled coma and the modelled starlight core together, then study what remains. If the subtraction leaves no sharp spike at the centre, only a smooth gradient, the nucleus must be smaller than the optics could have resolved. The absence becomes a ruler. Sharp optics above the atmosphere make this ruler more precise. Without the shiver of air, starlight contracts into a tidy shape that mathematics can describe with confidence. The coma profile is measured in concentric rings, the instrument's fingerprint is calibrated on nearby stars, and the two are combined to predict what a nucleus of a given brightness would do to the center of the image. If a nucleus that bright would have produced a visible cusp and none is seen, the brightness of the solid body is limited from above. Convert that brightness into size and albedo, and an upper limit emerges, a few kilometers across if the surface is dark in the way small icy bodies often are, smaller if the surface is unusually reflective. Photometry turns this logic into numbers. The recipe is old but sturdy. Translate a hypothetical nucleus magnitude into an absolute magnitude by removing the distance and phase effects. Then apply the relation that ties absolute magnitude to diameter through albedo. A darker surface demands a larger diameter to shine as brightly as a brighter one. Cometary nuclei tend to be sooty, with visual albedos near a few percent, but nature tolerates exceptions. Analysts therefore present ranges rather than a single figure, acknowledging that a bright crust of fresh frost or a dark crust baked by radiation would swing the answer. Thermal light adds a second yardstick that does not care much about albedo. Warm solids glow in the infrared according to their temperature and size. Mid-infrared instruments, given a clear view, can collect that glow through the veil of reflected light and turn it into an effective radius. The conversion is not trivial. Thermal inertia, surface roughness, and the beaming parameter that accounts for how heat is re-radiated all play roles. Yet these dependencies are better behaved than the optical ambiguity. A nucleus that is small has less area to emit from, and so, for a given temperature, it simply cannot produce much thermal flux. A nucleus that is larger cannot hide its heat. When thermal measurements exist, they speak with a clarity that balances the optical upper limits and collapses the range of possibilities. There is a third, subtler way to weigh a small world. Outgassing imparts a reaction force. In precise astrometry, that force appears as tiny deviations from the path gravity alone would draw. Fit those deviations with a standard non-gravitational model and an effective area-to-mass ratio appears. Combine that ratio with a guess at gas production, and the product becomes a mass estimate. The uncertainties are wide, because gas production is itself inferred from light, and vents are not uniformly placed or stable. Even so, when the measured deviations are small, the mass cannot be too low, and therefore the size cannot be too small unless the density is improbably high. This is not a direct measurement. It is a boundary set by dynamics. Rotation cooperates by setting another boundary. A strengthless rubble pile cannot spin faster than a period that depends on bulk density and shape. If the light curve reveals a rotation well above the danger threshold, the nucleus may be very small, very strong, or both. If it shows a rotation closer to that threshold, the nucleus cannot be much larger than the upper limit without risking structural failure. The argument improves if a hint of elongation appears, because elongated bodies feel stronger centrifugal stress at the tips. Thus, even diluted under a coma, the rhythm of brightness carries a quiet message about the size of the core. There are moments when nature offers more direct methods. A predicted occultation of a distant star by the coma can, if the nucleus contributes an additional sharp dip, give a chord across the solid body. Teams scatter along the path on Earth to record the star's light at high speed as the traveller slides across it. A handful of successful chords, aligned by accurate timing, draw an outline. The challenge is that the coma often dominates, smearing the event into a shallow trough. Careful filtering and high cadence can still tease out a nuclear signature when the geometry cooperates. When it fails, the non-detection strengthens upper limits. Radar would solve the puzzle with a single shout of returned power, but distance usually defeats it. A body that does not pass near Earth presents too small a target for radar's square law. The echo falls beneath system noise long before a shape can be drawn. Only exceptionally close interlopers reveal themselves to radio eyes, and then only if they do not drown the echo under a thick envelope of gas and dust. The absence of a radar solution is therefore not a surprise. It is the rule. Activity itself confuses size measurements and yet contains information about scale. A small nucleus with lively vents can sustain a dust coma that rivals the display of a larger, lazier body. The key property becomes the fractional active area, the fraction of the surface that is doing the work. If dust production inferred from AF rho is healthy, while the nucleus is tightly constrained from above, the active fraction must be high. That conclusion shapes the portrait of the surface. It suggests a network of accessible cracks and pits, and a crust thin enough to let heat reach volatile layers. If, on the other hand, production is modest, and the nucleus could be larger, the surface might be mostly inert with only small patches in sunlight feeding the coma. Porosity connects many of these threads. A highly porous interior lowers bulk density, shifts the rotational failure limit, alters how heat travels beneath the surface, and changes how non-gravitational forces translate into changes in motion. Porosity also affects thermal measurements through the beaming parameter, since a rough, fluffy surface can hide warm nooks that beam energy differently than a flat plate would. When models favor porosity, the range of allowed sizes tends to widen slightly at a given brightness, because the same illuminated area can look different to both optical and thermal instruments. Shape complicates the conversion from light to size. A sphere is a convenient fiction. Real nuclei are often elongated or bifurcated, which alters how much light they present as they turn. In thick coma, this modulation is damped, but not erased. If a small amplitude still appears, even after seeing and coma are accounted for, the underlying axis ratio can be bounded. The result becomes a family of solutions: a shorter long axis for a brighter albedo, a longer long axis for a darker one, all threaded through the same light curve amplitude and phase law. There is a restraint that honest work respects. Numbers, published with too many decimals, invite a confidence the sky has not granted. Good practice is to present the size as an inequality and a range, with the assumptions stated. Small enough that a pinpoint is hidden under the coma, large enough to carry the mass implied by motion and to stay intact at the measured spin. Likely dark, unless fresh frost or reflective crust is present, and therefore likely nearer the larger end of the optical estimate, possibly smaller if thermal data argue for it. This humility is not reluctance to decide. It is a recognition that a glowing envelope was built to hide what the question most wants to see. Even with that humility, the portrait sharpens. The heart is compact by planetary standards, measured in kilometers instead of tens. It is energetic enough to throw dust in stable patterns at safe distances from the Sunday. It is too small to resolve directly in reflected light with current optics at the present geometry, and too far for radar to outline. It carries a density that resists rapid spin without tearing, yet probably welcomes porosity that keeps weight low and heat cautious. It presents a surface that is not mirror bright, but not so dark that extinction swallows it completely. These sentences may sound qualitative, but together they establish a narrow habitat of possibilities in size. When the coma thins with distance, the same methods return for a second pass. A fainter envelope gives the point spread function room to stand taller, and the upper limit can drop. Thermal emission softens as the object cools, yet remains measurable for a while on the largest mirrors, refining radius estimates without arguing with albedo. Non-gravitational effects decline too, which freezes the dynamical bounds into a final value. This afterglow of measurement continues even as the object leaves human attention. By then, the size of the heart is no longer a mystery with an open horizon. It is a number with a margin, earned by images that learned how to subtract, by heat that could not hide, and by motion that carries mass in every centimeter of its curve. Expectations in comet science are not law, yet they are strong habits, and those habits begin with water. Textbook energy balance says that inside a few astronomical units, sunlight should push water ice across its sublimation threshold and turn nuclei into steam engines that carry dust outward. Production rates scaled with distance, phase-corrected magnitudes, and long-standing correlations between water and dust have been tuned to that view for decades. When a traveler insists on a different script, favoring carbon dioxide while water stays hesitant, the surprise is not theatrical, it is structural. The tools that observers and modelers reach for first suddenly fit badly in the hand. Thermodynamics explains how this revolt is possible. Vapor pressure climbs with temperature in steep exponentials, and each volatile writes its own curve. Carbon dioxide awakens at temperatures near 100 to 120 Kelvin, where water is still largely silent. Its latent heat of sublimation is lower than water's by a broad margin, so a given watt of sunlight can lift more mass of carbon dioxide than water at the same skin temperature. In the simple Hertz-Knudsen view, sublimation flux follows the product of vapor pressure and a thermal speed term, both of which favor carbon dioxide in the cold. A nucleus bathed in weak sunlight can therefore develop a coherent coma without asking water to help. That is not unprecedented in catalogues, but it is blunt enough here to make standard distance laws look naive. Surface physics adds a second lever. Sublimation can be limited by heat available at the skin or by the ability of gas to escape through a crust. A dust mantle only tens of centimeters thick can choke water while leaving carbon dioxide closer to freedom. Porous grains sintered by radiation create narrow pores where mean free paths and gas opacities play tricks with diffusion. Heat percolates down by centimeters, pressure builds in pockets, and vents open in places where sunlight favors microclimates. If carbon dioxide sits shallower than water because of prior processing, it will find the path first. This is a change of access rather than a change of inventory, yet to instruments it reads as a change of composition. The structure of the ice itself can deepen the divide. Amorphous water ice traps volatiles when it forms at very low temperatures. As that amorphous phase warms and crystallizes, it can release trapped gases in bursts that do not require liquid pathways or large pores. Clathrate hydrates add another possibility. Cages of water that hold carbon-bearing molecules and yield them when temperature and pressure slide across thresholds. Either architecture can vent carbon dioxide early and keep water modest until the thermal wave reaches deeper layers. In such a body, Activity is not a smooth ramp. It is a sequence of thresholds, with carbon dioxide crossing the line first. Coma physics then answers in kind. Gas temperature and molecular mass set terminal speeds of outflow. Carbon dioxide leaves more slowly than water at comparable temperatures, yet the higher mass flux that weak sunlight can support may compensate, delivering enough momentum to peel large grains off the surface. Dust size distributions shift under such engines. Heavy grains linger near the head, sculpting sunward fans and fat tails. Fine grains still depart quickly, but their share in the mass budget shrinks. Brightness gradients and AF row curves inherit that choice. A coma driven by carbon dioxide reads dust differently in the optical than a water storm would. The logistics of measurement magnify the surprise. Ground-based techniques often estimate water by watching OH at 308 nanometers, a proxy produced when water is split by sunlight. If water is weak, OH is weak, and classical pipelines undercount total gas. Carbon dioxide, whose strongest band sits near 4.26 microns, is a poor target from sea level because Earth's air contains the same molecule. Space-based spectrographs or rare windows at high, dry sites must be scheduled. An observing plan built around water pivots toward a plan built around carbon dioxide, and that pivot must happen while the geometry window is still open. The shock therefore arrives both in the physics and in the calendar. Dust grain chemistry is also folded into this inversion. Optical reddening often reflects organic skins laid on silicate cores by long radiation in the cold. Carbon dioxide-rich flows can loft grains with thicker coatings that survive gentle temperatures, keeping color slopes steady even as production rises. Water-rich flows nearer the sun can strip those skins, neutralizing color. If water never rules, color may remain consistently warm, and polarimetric curves may stay in the family associated with porous aggregates. In other words, the palette of the coma records the volatile hierarchy indirectly, and the record looks different when carbon dioxide is governor. Non-gravitational acceleration models must be retuned as well. Standard parameters that convert gas production into a tiny thrust implicitly assume water-dominated flow inside a given distance. Carbon dioxide changes the direction and duration of forces. It can act farther from the sun, where geometry and spin state differ, and its vents can hold steady while water would cycle more aggressively. Fits to precise astrometry that rely on familiar templates will misattribute small deviations if they do not account for a cold driver. Bias enters the ledger of mass, density, and active area from that single oversight. Origin stories absorb the jolt with interest. A body that speaks carbon dioxide with confidence may have formed near a carbon dioxide snowline in a young disk, where temperatures allowed that ice to condense as a primary. It may have built its crust from grains that migrated outward from warmer zones, then accreted coatings in a colder neighborhood, a sandwich of histories in millimeter layers. It may have inherited a higher carbon-to-oxygen ratio from its parent cloud. Each path leaves fingerprints in isotopes and minor species, ratios that can be measured if spectra are generous. The point is not that one path must be chosen. The point is that water silence and carbon dioxide eloquence immediately widen the plausible kitchens where such a body could have been baked. Photochemistry in the coma writes a final set of consequences. Carbon dioxide under solar ultraviolet light spawns CO and atomic oxygen with distinct line emissions and distinct lifetimes. The scale lengths of these products differ from those in a water world, so long slit measurements across the head retrieve different profiles. Filters designed for familiar radicals can mislead if they collect daughter products with altered parents. When the chemistry flips, the distance at which the coma becomes collisionless, the photolysis zones, and the ion tail architecture all reset. Plasma boundaries shift, pickup ion compositions change. The invisible weather around the body learns a new climate. None of this contradicts physics. It contradicts habit, the quiet assumption that water is the universal key within a few astronomical units was a convenience that held often enough to be useful. A nucleus that climbs into brightness under carbon dioxide reminds the field that convenience is not truth. The revision is productive. It pushes instruments toward wavelengths that had been left on the margin. It refines thermal models so that diffusion, clathrates, and amorphous transitions compete honestly. It forces dynamical fits to shed old biases. It teaches that volatile hierarchies are not fixed across systems, and that diversity is not noise but signal. There is a human undertone beneath the chemistry. A small world with a cold voice teaches patience in interpretation. It asks astronomers to watch for thresholds rather than rely on smooth curves. It asks modelers to let microstructure and processing write the rules at the surface. It asks schedulers to favor infrared when instinct says ultraviolet. The shock fades into method. The method becomes the new habit. In that shift, the science gains a wider vocabulary for how small bodies wake, breathe, and shed their skins under sunlight that is the same here as it was in another home, yet received by a crust that keeps its own counsel. In young planetary disks, invisible borders sort matter by temperature. Astronomers call them snow lines, each one the distance where a specific volatile prefers to live as ice rather than gas. Around a sun-like star, water freezes near a few astronomical units where mid-plane temperatures hover near 150 Kelvin. Carbon dioxide sets its own boundary, where the midplane cools towards 70 Kelvin, often several AU farther out. Carbon monoxide chooses colder ground still, tens of AU for a typical disk. These borders are not fences. They migrate as the star dims and the disk thins, and the fog of tiny solids drifts inward carrying ices across the thermal map. Yet the broad cartography holds. If a small worldlet assembled near the carbon dioxide line, its stones would be salted with that ice from the start. If it formed elsewhere, then slept in interstellar night, surface chemistry could be rewritten until water lost its advantage at first light. Begin with the nursery option. Pebbles grow in cold midplanes where grains collide and stick. As they drift through the carbon dioxide line, they collect mantles rich in that molecule, either as a primary condensate or as product of reactions on grain surfaces where carbon monoxide meets oxidants and locks into a more stable form. Clumps sink toward pressure traps, then accrete into kilometre bodies with a patchwork of layers that record where each batch of pebbles once lived. Such bodies carry a memory of a middle realm. They are poor in minerals that only condense hot. They are rich in ices that condense at modest chill, with carbon dioxide keeping close company with water and more volatile species hiding deeper or escaping early. This scenario writes expectations into the present. Volatile inventory would favor an early rise of carbon dioxide under weak sunlight. Water would require either more heat or fractures that reach layers where it is trapped. The first coma would be granular rather than gossamer because carbon dioxide can loft large grains even while water sleeps. Isotopic ratios would cluster near values expected for ices built at tens of Kelvin, including a carbon fraction that reflects chemistry on grain surfaces rather than gas phase paths. The color of dust would lean toward warm slopes, an imprint of long processing without deep reheating. None of these traits are exotic. They are the signature of a body that formed in a band of the disk, where carbon dioxide was easy to make and hard to lose. Now shift to the second possibility, a cooked shell. Interstellar space is quiet in density and loud in radiation. Ultraviolet from hot stars and galactic cosmic rays from ancient shocks rain for ages on small bodies. In laboratories, mixtures of simple ices exposed to such fields turn dark and polymerize into complex organics. Grain surfaces coat themselves with thin skins that are optically active and mechanically stubborn. Over long spans, micrometeoroid impacts and radiolysis can knead these skins into an insulating crust measured in millimeters to centimeters. The crust blocks pores, lowers permeability, and changes how heat and gas move. Water evaporates reluctantly through such a skin, while carbon dioxide, stored in shallower pockets or released by rearrangement of bonds, finds expression earlier. The surface reads like a varnish laid down by time. It does not care that water is plentiful underneath. It cares about access. Thermal physics supports this shell. The diurnal skin depth that feels day and night is only a few centimeters for a porous mix typical of comets. If thermal conductivity is near 1/100th of a watt per meter Kelvin, the density a few hundred kilograms per cubic meter, the heat capacity a few hundred joules per kilogram Kelvin, and the rotation period measured in hours, a simple calculation puts the depth of significant temperature swings near 2 centimeters. That is shallow. If the crust is thicker than that, water beneath remains cold, even while the surface warms and cools. Carbon dioxide stored or generated within the skin rides the daily cycle first. Gas diffusing from deeper reservoirs must cross a maze that the shell has tightened, and it does so slowly until heat builds enough to pry new paths. Two variants of the cooked shell make the story more interesting. The first is amorphous to crystalline transitions in water ice. When water ice forms at very low temperature, it can trap other molecules within its disordered lattice. Warm that ice, and it crystallizes, releasing guests in pulses. If the crust contains such amorphous pockets, warming can liberate carbon dioxide in discrete steps that do not require the deep layers to participate. The second variant is clathrate hydrate, where water forms cages that imprison carbon-bearing molecules. Clathrates dissociate when pressure drops or temperature rises, again delivering carbon dioxide before bulk water flow dominates. These architectures put chemistry into the shell itself. They make the crust a machine rather than a mere lid. Sintering joins the cast. At temperatures approaching the softening point of water ice, grains begin to weld at contact points. Net growth reduces porosity and locks grains into a stronger, less permeable fabric. Even a few degrees of heating sustained for days can change the leakiness of the surface. If a worldlet has wandered close to a star before, shallow layers may already have experienced modest sintering and annealing. Those layers would act now as a throttled sieve. In that case, the timing of increased activity might reflect the stepwise failure of welded networks as thermal stresses crack them open. Each pathway carries predictions that observers can test. A nursery near the carbon dioxide line implies stability in the volatile hierarchy across the passage. Carbon dioxide should dominate early and remain proportionally important even as the sun draws near, unless water layers become directly sunlit. Isotopic ratios in carbon and oxygen would sit in ranges sympathetic to cold formation in a disk, and minor species that form through low-temperature pathways should join the spectra. A cooked shell implies evolution. Early carbon dioxide would be strong, then perhaps plateau as deeper heat activates water through newly opened pores. Outbursts would be more likely when thermal stress fractures the varnish. Color maps could trend slightly bluer in the inner coma at such times as fresh, less processed grains are exposed and shed. Polarimetry would record changes in texture as compact crust fragments give way to fluffier interior material. Geometry of activity offers another discriminator. A body whose character is set by a primordial volatile mix may exhibit a broad belt of vents that track the subsolar latitude smoothly. A body whose shell rules may instead show activity funneled into discrete pits and chasms where the crust failed. Such structures sometimes reveal themselves as repeated fans, anchored to fixed position angles that brighten and fade with rotation, yet do not migrate much over weeks. High-resolution imaging from space can catch these patterns in the inner few thousand kilometers, turning a qualitative sketch into a map with measured angles and widths. Thermal emission from the nucleus helps, even when diluted by the coma. A low beaming parameter and muted phase variation in thermal light point to a rough, porous surface that mixes hot and cold microfacets. A higher beaming parameter with smoother phase behavior suggests a skin that behaves more like a cohesive sheet, redistributing heat and emitting less directionally. Neither measurement is easy under a bright coma, but even partial results nudge the model toward one interpretation. Chemistry of the coma downwind from the head can also betray the structure above the vents. If the shell fragments into chips and plates, the resulting grains have different aerodynamics than fragile aggregates. Mass-sorted fans and curvature of synchrones would shift accordingly. The fragmentation rate with distance, measured as changes in the slope of surface brightness profiles, tells whether grains are robust clasts or delicate knots of dust and ice that fall apart quickly. A cooked shell tends to supply the former before exposing the latter. There is a temptation to pick a single origin and pin it to the traveller like a badge. Patience suggests a blend. A world born near a carbon dioxide line could still spend long centuries in interstellar night building a varnish. A world formed somewhat inside that line could inherit carbon dioxide through clathrates and then protect it with a skin. The clean categories blur in the lived physics of small bodies. What matters is whether the evidence favours shallow sources and a controlling shell, or a deeper, well-mixed inventory that simply follows its own vapour pressures. With time, both options become testable. The last piece in this puzzle is time itself. Disks cool over millions of years. Snow lines sweep inward. Bodies born early record wider separations between water and carbon dioxide zones than bodies born late. If the visitor grew quickly and left its cradle soon, its chemistry might reflect a hotter epoch and a cruder layering. If it grew slowly in a quieter disk, it could be more uniform. Interstellar transit writes yet more time into the surface through radiation and microcratering. These clocks are not precise, but they tick in the right order to guide a narrative from nursery to night to present sunlight. Put together, the hypotheses feel less like rivals and more like chapters. Snow lines script the first draft by allotting ices to radii. Varnish edits the draft by hardening the opening pages. Sintering binds, clathrates release, amorphous ice remembers, and cracks decide when memory becomes breath. The object that now crosses inner distances carries all of these processes in miniature. Its face is a compromise between where it learned to be cold and how long it stayed that way. Its present voice, heard in gas and dust, is the sum of a birthplace and a shell that kept secrets until the right warmth arrived. Galactic cartography begins with a question that sounds simple. What kind of star field does the traveller belong to? The Milky Way divides its citizens into broad populations that move with different tempers. One is the thin disk, a cool river of stars that hug the midplane, young to middle-aged, with gentle random motions around a dominant rotation. Another is the thick disk, older and puffier, its members lifted above and below the plane with higher dispersions in all three velocity components. Beyond those layers lies the halo, a sparse rain of very old stars that roam with little regard for the spin of the galactic wheel. A body that arrives from interstellar space must have ridden with one of these communities, or crossed them on business, set by long-ago ejection. The difficulty is knowing which, when all that can be measured is a single velocity near a single star. The arithmetic of membership begins by removing the sun's own drift. Observers transform the measured motion into the local standard of rest, the average flow of nearby stars. In that frame, the velocity is written as three numbers that point toward the galactic center, along the galactic rotation, and toward the north of the galactic plane. Thin disk stars cluster near modest values with small scatter. Thick disk stars spread wider and run slower in rotation by several tens of kilometers per second. Halo stars scatter broadly with little sense of the disk's spin. Place the traveller's point on that three-axis map, and the temptation is to circle a label. Temptation should be resisted. A single point lacks the context that millions of stars provide. The map was built for statistics, not for verdicts on one body caught in passing. Selection effects thin the evidence further. Surveys that discover fast visitors do not watch every direction with equal vigour. They must avoid the sun's glare and the crowded bright river of the Milky Way where confusion is high. They favour seasons and latitudes set by weather, engineering, and human schedules. Directions that lie near the headwind created by the sun's motion through the local stars are easier to search because gravitational focusing lifts flux there. Those biases can shift the apparent mix of velocities in the sample of interstellar bodies that are actually found. A single object embodies those biases without telling which ones dominated. Any label attached to its motion carries that ambiguity quietly. Dynamics inside the solar system also blurs the handwriting. The sun alters the path of an interstellar object by bending the inbound line into a shallow turn. Planetary gravity adds tiny flavors of deflection. Outgassing can decorate the curve with subtle non-gravitational nudges. Analysts can remove these effects to recover the asymptotic velocity at infinity, but uncertainties remain. A few meters per second written onto the outbound vector propagate into several kilometers per second of uncertainty when translated into the galactic frame. That spread may be small compared to the differences between thick disk and thin disk dispersions, yet it is not zero. On the Toomri diagram, where speeds are visualized as distances from the thin disk origin, that small uncertainty can slide a point across the soft boundary. Chemistry of the parent stars is often used to separate the disks. Thick disk members trend older, with higher abundance of alpha elements relative to iron, and often lower overall metallicity. If small bodies inherit their volatile inventory from such environments, some statistics might appear in the comae of interstellar visitors. Ratios of isotopes in carbon and oxygen, or the presence of minor species favored in metal-poor chemistry, could in principle whisper about a parent star's lineage. In practice, the answers are muted. Coma, spectra, measure materials that lived on and within tiny grains, where local disk chemistry and surface reactions dominate. Global metallicity labels do not flow easily down to molecules trapped in pockets of ice. Even a perfect spectrum would offer only soft hints. Kinematic heating over time complicates every label. Thin disk stars do not keep their birth motions forever. Encounters with spiral arms and giant molecular clouds stir them gently. Over billions of years they drift upward in dispersion. Some migrate radially. The line between old thin disk and thick disk is therefore a fence drawn through a field where footprints cross. A body ejected early from a thin disk system could carry the motion of an old thin disk star, even though its parent belonged to a population that would be classified differently today. That mismatch of label and history is baked into the galaxy and cannot be removed by local measurement. There are also moving groups and streams, small families of stars that share a common motion. Some are debris from dissolved clusters, some are dynamical resonances carved by the bar and spiral pattern. Their kinematics can mimic membership in one disk or the other, while their ages and chemistries map elsewhere. If an interstellar fragment left such a group, its velocity would ride with the group without offering any hint of its specific birthplace. A single point cannot tell whether it belongs to a smooth population or a filament inside it. Only a crowd tells the difference, and a crowd of interstellar comets does not yet exist. On the theoretical side, ejection efficiency depends on the architecture of the birth system. Giant planets near the snow lines create slings that fire planetesimals out of the natal fabric. Binary stars perform the same work with even fewer conditions. The rate at which a system exports debris scales with the number and mass of perturbers and with the duration of the unstable epoch. Thick disk stars tend to be older, which leaves more time for instability to have burned out. Yet older age does not erase the early bursts of ejection that would have populated interstellar space long ago. The present-day velocity simply measures the river on which the fragment has drifted since. It does not remember the hands that threw it in. Models that count how many interstellar fragments should pass through a sphere around the Sun must fold all of this together. The density of sources in each disk, their export rates, the time over which fragments remain intact, the gravitational focusing of the Sun, and the efficiency of discovery across directions and magnitudes all enter. Change the assumed longevity of small icy bodies under cosmic rays by a factor of 2, and the population mix at the Sun changes. Change the rate at which wide binaries break up, and the ejection budget changes. Any attempt to pin a single object to a parent population must admit that such models are exploratory. They are an honest guide for averages, not a stamp for one visitor in one season. There are tiny clues that can add texture to a cautious answer. If the speed relative to the local standard is very low, the body moved almost lockstep with typical thin disk stars. If it is modestly higher, the thick disk's wider dispersions become plausible. If it is extreme, the halo comes into the conversation. If the incoming direction aligns with the solar apex, discovery bias is salted in. If not, the case grows cleaner. If the orbit plane crosses the galactic plane at a steep angle, the vertical component of velocity is substantial, a trait more common outside the thin disk. None of these clauses escape the problem of single data points. They only add shading. A philosophical adjustment helps the analysis. The goal is not to assign heritage as if a passport were hidden under the dust. The goal is to ask what range of galactic neighborhoods could plausibly produce an object with such a speed and direction, and to rank those neighborhoods by simple measures. Thin disk can be likely by sheer numbers, since it outnumbers the thick disk locally. Thick disk can be competitive through larger dispersions that fill the wings of any velocity distribution that intersects the sunday. Halo can be rare, but not impossible. In that ranking, the label chosen for one case is less important than the practice of expressing the uncertainty honestly. Future statistics will repair much of what is thin today. A few dozen interstellar bodies with well-measured asymptotic velocities would let a population diagram be drawn in the same space used for stars. Clustering would appear if moving groups contribute. A smooth cloud would appear if random ejections from the field dominate. Anisotropy would signal survey bias and solar headwind focusing. Even a handful more points begin the correction. The present moment does not offer that corrective power. It encourages humility. And humility is not a weakness in science. It is the discipline that keeps speculation from hardening prematurely. For the single traveller in hand, the label thick disk remains a possibility written in pencil. So does thin disk. Each can be made to fit within uncertainties and biases. The evidence is a vector, a set of transforms, and cautious removal of local forces. It is thin by the standard of stellar surveys that command millions of points. It is thick by the standard of a field that had nothing to plot only a short time ago. The best sentence is the simplest one. The velocity is compatible with the kinematics of ordinary galactic citizens. The rest must wait for statistics that turn arithmetic into pattern. Population is a quiet word for a large idea. A single traveller dramatizes the sky. Many travellers, even if seen one by one, begin to outline a census. The question is simple and deep. How many fragments of other suns drift through the neighbourhood of this star at any given time? And what kinds of fragments are they? The answer is not printed on any image. It is inferred from the machinery of discovery, from the shapes of curves on detectors, and from the absence of detections in places where telescopes looked hard and found nothing. The arithmetic starts with an effective search volume. A survey of given depth can see an object of given size and reflectivity only inside a bubble whose boundary depends on brightness, phase angle, and motion blur. That bubble is not a sphere, it is a lopsided region that shrinks near twilight, trims itself where the Milky Way saturates the field with stars, and fades where weather, moon, and scheduling remove nights from the ledger. Multiply that volume by the time the survey spent watching, then divide detections by the product, and a first estimate of space density appears. Every symbol in that estimate carries biases that must be dragged into daylight. Brightness sits at the center of those biases. An inactive shard is visible only by reflected sunlight. Its reach grows with albedo, and cross-section and shrinks with distance. A dusty body enlarges its cross-section with a coma and tail, and wins a longer detection range. That single fact tilts early samples toward classic comets and away from quiet stones. The population in space is not dominated by dust makers simply because surveys find many of them first. The population in data often is. Correcting for that tilt requires models of activity that describe how coma brightness rises with solar distance for a family of volatiles, and that correction changes as phase angle and forward scattering change. Motion blurs images and costs discoveries. A fast visitor streaks across a long exposure, and its light smears into a thin line that automated pipelines may reject as an artifact. The cure is short exposures and stacks that follow the moving target, but not every survey is built to do that every night. Trailing loss carves out an invisible wedge of missed objects at high apparent rates. That wedge is largest near closest approach, and near opposition where objects move most quickly on the sky. Surveys that are sensitive to streaks can reclaim some of that loss, but the correction remains an honest piece of the uncertainty budget. Direction matters in two quiet ways. The sun's gravity modestly focuses interstellar traffic into a headwind and a lee, increasing the flux of visitors that approach near the solar apex and decreasing it behind. Survey footprints are not uniform either, for practical reasons. Together these effects make some radiance more productive in detections even if the sky beyond is uniform. Without careful modelling, a genuine anisotropy in space can be mistaken for bias, and bias can be mistaken for structure. The cure again is arithmetic, not romance. Fold focusing and footprint into the estimate, then ask what isotropy looks like after those folds. Size distribution is the next lever. Populations of small bodies often follow power laws where the number of objects grows steeply as size shrinks. In such families, a handful of large, bright members are rare but easy to find, while an ocean of small, faint ones are common but hard to see. A sample of a few young detections tells little about the slope of that power law. One can sketch families of curves that would match the data and still be wildly different in total mass. Until dozens of objects across a range of sizes are found, the slope will remain an educated guess. Even so, the presence of both a small, nearly inert interstellar shard and a larger, strongly active comet signals that nature populates multiple rungs on the ladder. Survival in interstellar space sets a ceiling on what the population can be. Dust mantles darken under radiation, volatile skins desiccate, and micrometeoroid gardening sand surfaces. Erosion rates are low compared to comet activity near a star, but the timescales are long. A fragment must resist crumbling for millions to billions of years if it is to be counted in today's flux. Strength, porosity, and chemistry decide that fate. If only certain architectures survive, the detected population will reflect that survival bias. Bodies with delicate internal ice structures may vanish into fine dust long before they can be seen at another star, while compact aggregates with robust crusts endure and arrive. Production must pay for survival. Young systems export fragments during periods of dynamical unrest. Giant planets scatter planetesimals. Migrating resonances churn belts. Binary stars eject with ruthless efficiency. The export rate per system is the product of how much solid mass is available, how long instability lasts, and how often patients in the scattering ward are discharged rather than readmitted to stable orbits. Integrate those exports across the density of stars in the galactic disk, and a background flux appears. Matching that flux to the local detection rate sets constraints on how generously systems must eject. If the inferred density of interstellar fragments is high, then either many systems export energetically or a smaller fraction export, but with extraordinary yield. A different line of inference runs through non-detections. Surveys have spent wide swaths of time looking deep near elongations that favour discovery. The absence of a swarm of small, inert interstellar asteroids inside those data means that the number density of very faint bodies cannot be arbitrarily large. Upper limits derived from quiet archives are as important as the few detections that drew headlines. They shave the high tail from population models that would otherwise explode into implausible counts. Future cameras will refine everything. A wide field survey that covers most of the accessible sky every few nights, with deep limiting magnitudes, is a machine built to erase bias. Uniform cadence, better streak handling, and rapid alerts will catch faint interstellar passes earlier on approach, when rates are slow and phase angles are kind. Early discovery lengthens the spectroscopic window. It also makes time for precision astrometry, that cleans the asymptotic velocity and fixes the radiant with smaller cones of uncertainty. Even a handful of such early finds can reduce population error bars that now span orders of magnitude. Population is not only a count of stones and ices, it is also a distribution of chemistries. Some fraction of fragments carry volatile inventories that wake far from any star. Some fraction carry only tight reservoirs that breathe faintly, if at all. Some carry abundant organics near the surface, others lock organics behind crusts. If disk chemistry varies with distance from the star and with the ratio of carbon to oxygen in the natal cloud, then the set of interstellar visitors will sample that variation in a way no single planetary system can. A population of spectra becomes a map of what disks chose to make, integrated over many kitchens. Capture events sit at the edge of this subject. A fast interstellar body rarely slows enough to be bound by a single pass. Yet tiny fractions of the flux can be captured by three-body encounters or by drag in extended envelopes around giant planets. Those captured members would masquerade as very long-period comets with odd chemistry and slightly odd dynamics. Their numbers should be low, but not zero. Population models that predict captures invite targeted searches for outliers in the catalogue of barely bound comets. Finding even one genuine capture would place a stiff constraint on the incoming flux and on the velocities that dominate it. Missions that wait in readiness add an experimental thread. A spacecraft parked on a deep space orbit, supplied with fast response propulsion, could sprint to intercept a newly discovered interstellar object at modest relative speed. The probability of a rendezvous within constraints set by fuel and time depends on how often such objects appear within a certain corridor of approach geometries. That probability is the population problem written as engineering. Higher flux and broader radiant distributions translate into more windows a mission can exploit. Designing those missions requires the same numbers that astronomers try to extract from surveys, only expressed in units of delta V and weeks. A philosophical consequence blooms from the dry arithmetic. If the space density of interstellar fragments is large, then all mature planetary systems bathe in a slow rain of foreign material. Rare grains enter atmospheres and oceans on worlds that can host oceans. Rare pebbles graze moons. Rare comets pass through outer reaches of systems and leave faint trails of dust. The exchange is not a directed mail, yet it is a commerce of material and molecules. Even if biology is not carried, prebiotic inventories are, and the traffic makes the galaxy feel a little less parcelled into isolated farms and a little more like an archipelago of islands that exchange driftwood. The problem, then, is not a puzzle with a single key, but a network with many small locks. Rate, bias, size, survival, production, chemistry, capture, mission design, and meaning all link to one another. Each new detection turns one more warded lock. With every turn, the portrait of the invisible population sharpens. The sky will never be crowded with these wanderers to the human eye. To instruments and patient statistics, the crowd is already present, waiting to be counted with care. Strange patterns invite grand explanations. A sunward lobe of dust, a coma that prefers carbon dioxide to water, metal lines that favour nickel while iron stays muted. Each of these can sound like a whisper from unfamiliar physics. The temptation is to summon new forces with new names. Patience suggests another path. Begin with geometry and chemistry, the reliable artisans of comet behaviour, and ask how far they can travel toward the odd before help is needed from the exotic. The smallest deviations in a track across the stars are the crucible for wild ideas. If the path bends more than gravity allows, one can blame radiation pressure on the whole body or the recoil from outgassing. Radiation pressure is real, but its push on a compact kilometre-class nucleus is feeble. To move the solid heart appreciably, the area must dwarf the mass, a ratio suited to foams and films, not to porous rock and ice. Outgassing, by contrast, is a thruster that nature installs for free. When gas leaves preferentially from one face, The nucleus feels a steady breath of force. The direction of that breath is not arbitrary. It leans sunward when the warmest vents face day, sweeps sideways as rotation carries them into afternoon, and softens at night. A fit that allows for this threefold pattern in the equations of motion will either absorb the anomaly or leave a residue that demands imagination. The cleanest cases leave little residue. Radiation pressure still rules, but on dust. Large grains launched with a modest kick can travel sunward for hours before light shepherds them into the antisolar flow. Fine grains surrender immediately and draw the more familiar feathered tail. A sunward wedge near the head is therefore less a violation than a census of sizes. The geometry of observation sharpens or dulls the wedge. Forward scattering at certain phase angles fattens the inner coma and makes the lobe obvious. Cross the orbital plane, and a sheet of particles seen edge-on pretends to be a spike pointing up the sun's line. These are illusions of arrangement, not announcements of new dynamics. Chemistry writes similar corrections. Carbon dioxide sublimates at colder temperatures than water and can lift dust before water wakes. If the crust contains shallow stores of that molecule, or if clathrates and amorphous ice release it in pulses, the coma becomes lively far from the distances where water sets the schedule. The same flows that carry dust will also carry trace atoms liberated from grains. Nickel's lines shine if it is freed into the neutral gas, and if sunlight pumps its transitions efficiently. Iron can fail to answer not because it is absent, but because it sits in tougher lattices or hides in phases that resist photodesorption at the temperatures achieved. Resonant fluorescence introduces a further tilt. If solar line structure favors nickel's transitions over ions in the bandpass used, brightness will exaggerate a modest abundance difference. None of this requires unusual physics. It requires chemistry under low temperature and low pressure, and an awareness that the sun is a structured lamp, not a white blaze. Thermal geometry is an old sculptor of mischief. The nucleus with vents near its subsolar belt will beam material in a pattern tied to latitude and season. Rotation modulates that pattern with a clock. A rough shape with cliffs and pits will self-shadow, creating micro-dawns and dusks within a single spin and switching jets on and off like a metronome. The inner coma records these beats as faint ribs and fans that appear to lean the wrong way when projected onto a flat sky. High-cadence imaging exposes the rhythm and erases the illusion. The same rhythm, folded through a precise light curve, turns into a map of active longitudes without declaring any new force. Electrostatics occasionally enters the conversation as a rebel. Photoelectric charging on sunlit surfaces can loft submicron grains at a few meters per second in weak gravity. Lorentz forces then guide those charged particles along plasma drifts, drawing delicate rays that early observers might mistake for unusual gas behavior. The scale of the effect, however, belongs to very small particles and small volumes near the head. The bulk of a dust lobe composed of millimeter and centimeter grains will ignore electric shepherding and obey gas, drag, inertia, and sunlight. Electrostatic embroidery can hover at the edge of the picture without owning the canvas. A different class of proposal invokes hidden engines inside the nucleus. Radiogenic heat in a small ancient body is too weak to matter. Exothermic crystallization of amorphous water ice does matter, and it can mimic outbursts by releasing stored volatiles rapidly as the lattice rearranges. Clathrates can dissociate, paying a latent heat and uncorking gases in sudden breaths. Both mechanisms are classical. They widen the range of behaviors available to a cold object warmed unevenly. When seen late and pieced together from scant data, their signatures can look like novelty. Seen early and followed with attention, they settle into the ledger of expected surprises. Measurement itself can conjure ghosts. Telluric absorption skims away parts of spectra at the wavelengths where carbon dioxide speaks, turning weak features into riddles if calibration is casual. Deconvolution of the inner coma can install a false cusp where no nucleus is seen, or remove a real one if the point spread model is imperfect. Astrometric centroids can wander under variable, seeing as light from jets lifts and falls, imitating tiny accelerations. The cures are plain, though not always easy. Standard stars, stable instruments, repeated nights, multiple teams. When they are applied, the exotic contribution often shrinks. Practical predictions divide simple physics from romantic elaboration. If outgassing drives small deviations in motion, the amplitude of those deviations should follow the solar distance roughly as a power law tied to sublimation and geometry, and the direction should wobble with the season of the subsolar point. If radiation pressure on a low-density blanket were somehow responsible for bulk acceleration, the signal would not switch sign with rotation and would scale with cross-section in ways that conflict with size limits. If nickel is favored by release chemistry, its line strength should change as thermal regimes shift and fresh surfaces are exposed, while iron slowly emerges if deeper, sturdier hosts begin to erode. If pumping dominates, line ratios should track solar velocity and phase more than production. Each of these trends is testable with patience rather than novelty. There remains room for genuine strangeness, but strangeness must earn the right to stand. Fractal aggregates with astonishingly high area to mass ratios can exist in dust populations and change how radiation and gas push them. Rocket grains that carry embedded ice continue to accelerate after launch as they vent, bending synchrones and syndynes subtly away from textbook curves. Plasma boundaries can flicker under solar wind changes and momentarily redirect ions and the finest dust. These are not coalitions of unknown forces. They are fringes of known ones, operating where materials are fragile and time is short. The sensible arc of explanation begins with a checklist. Geometry first, phase angle, orbital plane crossings, and projection. Chemistry next. Volatile inventory, trapping mechanisms, and photolysis. Thermal structure and topography for the engine room. Electrodynamics for embroidery, calibration for humility. If a signal remains after that list is honoured, then the door opens to new ideas. Often it closes again with a soft click as more data arrive. It is easy to mistake rarity for novelty. Interstellar fragments are rare visitors, so their habits can feel new simply because the circumstances of their birth differ from local norms. Different kitchens bake different crusts. Different winters carve different pores. The same sunlight that rules nearby comets learns new paths through unfamiliar skins. In that light, odd forces dissolve into ordinary ones applied to uncommon materials. What remains is not disappointment, but refinement. A sunward dust fan becomes a ledger of sizes and launch speeds. A carbon dioxide-led coma becomes a thermometer that reads shallow layers long before water stirs. Nickel lines become a tracer of surface chemistry and solar pumping. Gentle drifts from gravity's road become a measure of vent, geography, and spin. The worldlet keeps its mystery, but the mystery is framed by tools that already exist, sharpened by careful use. The discipline is to hold two thoughts at once. New physics is precious and rare. New combinations of old physics arrive every season in the small, fragile laboratories that wander past the Sunday. Honour the second first. Let the first wait until patience has done its work. In the quiet that follows, the sky often reveals that the strange was simply the familiar, viewed from a new angle, on a body made in a colder kitchen, with a skin that kept its secrets until the light found the right seam. Life is a word with edges, and the sky touches those edges with the gentlest of tools. A small body breathes beside a star, and the breath carries molecules that can be counted, weighed by their light, and placed on a chart. Some of those molecules feed biology on warm worlds. Some are only the raw syllables from which chemistry composes meanings later. The distinction is hard to draw at a distance. Instruments do not hear intentions, they hear bonds. Remote spectra sort the possibilities into families. Volatile organics show in the near and mid-infrared where bond vibrations take their steps. Simple alcohols, aldehydes, and nitriles mark one family. Aromatics and long chains mark another, often through broad bands that hint at rings and stretches rather than clean lines. Each detection is a clue to processes that worked on icy grains in the cold of a protoplanetary disk. Ultraviolet photons carve and rearrange. Cosmic rays stitch fragments. When sunlight finally warms the surface, trapped products lift out and write thin signatures in space. If those signatures rise above the low hum of dust, a case can be made for a cargo of prebiotic ingredients. Dust itself offers a second archive. Refractory organics coat mineral cores in films that resist heat better than the more fragile volatiles. Scattered light in the optical and near-infrared tends to take on a gentle red slope when such films are present. Polarization curves tilt in ways that favor porous aggregates dressed in complex skins. Thermal emission at longer wavelengths carries broad features that fit mixtures of amorphous silicates and carbonaceous matter. None of this is an announcement of life. It is an announcement that the feedstock for life can form without life. That statement matters more than it first seems. The question that follows is practical. Can biology itself ride inside a traveler that spends long ages between stars? The odds are cold. Radiation doses in interstellar space climb over millions of years to levels that sterilize unshielded microbes, many orders of magnitude beyond survivable limits. Vacuum desiccates. Heating during close solar passages spikes enough to stress any pocket that reached warmth. Only deep interior chambers, meters beneath the surface, would feel protection strong enough to preserve complex structures for comparable spans. A small worldlet that ventilates under sunlight is a poor vault. Cracks offer paths for heat and gas. Sublimation opens pores. The interior is not a solid sphere, but a woven framework where safe depths shrink. Chemistry does not carry that burden. Molecules many carbon atoms deep can survive, where cells cannot. Laboratory work on ice mixtures exposed to ultraviolet light has shown that simple gases, when frozen together, are coaxed into chains and rings that resist time. Glycine has been reported in comet samples returned to Earth. Amino acid precursors and sugars have been synthesized in cold chambers that mimic the births of comets and planetesimals. Formamide is a quiet celebrity in this literature, a reactive bridge between very simple species and the alphabet of prebiotic pathways. If a traveler lifts that molecule from warm fractures, its lines would strengthen the case that chemistry has been busy in the dark. Isotopes are the sober judges. Ratios of deuterium to hydrogen in water and organics, or of heavy carbon and nitrogen to their lighter partners, carry memories of the temperatures and radiation fields under which molecules formed. Biology on Earth prefers certain fractionations when it processes carbon and nitrogen, but those preferences overlap with values produced by low-temperature chemistry on grains. A decisive isotopic marker for life in a cometary coma remains a wish rather than a method. Still, measuring these ratios sketches the kitchen where the molecules were cooked. Cold environments build deuterium excess. Warmer ones dilute it. A profile of isotopes across species tests whether organics arose together or from separate layers of history. Chirality is the dream that cannot be reached remotely. Life on Earth chooses left-handed amino acids and right-handed sugars. Meteorites that fell on Earth sometimes carry small excesses of the same handedness, a hint that polarized light in star-forming regions may bias chemistry before biology had a voice. There is no way to read such a bias in a gassy coma from afar. Spectra do not deliver the handedness of a molecule across space. Only a sample return would carry that secret to a lab. Without it, detectives of life must settle for less decisive but still meaningful signs of complexity and synthesis. False positives crowd the stage. A strong band near 3.4 microns speaks of CH stretches in aliphatic chains. On a warm world coated with soot from engines, that band might betray industry. In a coma, it betrays only carbon bonded to hydrogen in a simple way. The same caution applies everywhere. Complexity is not intention. Long molecules do not imply genomes any more than a dictionary implies a poem. The right question is modest. Does the inventory contain pieces that, if delivered to a planet with oceans and energy, could engage in cycles that build further complexity? The answer to that question can be yes, without summoning anything sentimental about life adrift on ice. Delivery belongs to that modest frame. A hyperbolic parser sheds dust that crosses planetary orbits. The densities are thin enough to be harmless to spacecraft, but even thin streams drop grains onto atmospheres. Most burn. The smallest settle. On a world with oceans, the settled fraction joins an immense pool where chemistry runs by accidents and repetition. The fraction is tiny compared to local production. It is not zero. Over geologic time, the external contribution is a drizzle that writes one more term in a long equation. Across a galaxy, that drizzle is a chorus of faint voices, not a sermon. Testing the inventory wants a coordinated set of instruments. Mid-infrared spectroscopy can hunt for broad bands of complex organics and for the strong vibrational lines of carbon dioxide, carbon monoxide, and water that provide context. Near-infrared spectrographs can measure simpler organics and watch temperature-sensitive line ratios that translate into coma conditions. Millimeter arrays can follow resilient species like hydrogen cyanide and formaldehyde that trace deeper sources and can map velocity fields that tie chemistry to vents. Polarimetry can tag the textures that go with organics on grains. None of these tools can write biology onto a spectrum. Together, they can write a biography of molecules that a warm world would recognize as useful. Non-detection is as informative as detection. If searches set tight upper limits on common cometary organics while dust remains abundant, then the surface may be older, more processed, and less generous with soluble carbon. If organics appear but water remains shy, then the cargo likely lives close to the surface where gentle volatiles carry it into space early. If organics rise only when vents crack in sunlight near closest approach, then deeper layers contribute in episodes rather than in a steady exhale. Each pattern turns the general question into a set of specific maps of where certain molecules live inside a small body. Speculation often leaps from these maps to the story of panspermia. The careful version sets aside living cells and asks about chemical panspermia instead. Could molecules assembled under cold light in one system be spread to many and seed surface chemistry elsewhere? The answer leans yes in principle and small in practice. Scale and time place hard limits on delivery rates and survival after entry. The galaxy does not exchange packages. It sheds sawdust. That sawdust can be useful where circumstances are already favourable. It cannot replace local work. There is a softer value in all this. An interstellar fragment that exhales organics confirms that complex molecules are not rare accidents chained to a single sun. It shows that chemistry runs to richness whenever ice, dust, and radiation are allowed to argue for long enough. It suggests that when planets settle into quiet orbits and oceans condense, the ingredients they carry have already been rehearsed in a theatre older than their skies. A negative answer would also teach. A coma thin in organics would counsel humility about the diversity of kitchens in the galaxy, and the need to measure many examples before drawing a map. The final posture is patience framed by clear tests. Look for key carriers like methanol, formaldehyde, hydrogen cyanide, and formamide. Measure isotopes across multiple species. Map organics against dust, color, and polarization. Track changes with solar distance to see which layers speak when. Write down limits as carefully as detections and let them shape models of formation and processing. The traveler will not tell a story of life. It can tell a story about the preface to life, the chemistry that waits for warm water and time. That story's worth collecting, because it turns a bright smear near a star into a lesson about how many kitchens in the galaxy can set a table rich enough for later courses. Astronomy answers brief apparitions with coordinated haste. Schedules bend, cues reshuffle, and mirrors that usually dwell on slow programs turn to a point that will soon be gone. The plan is simple in outline and intricate in execution. Catch the volatile breath before glare overtakes it. Resolve the inner 1,000 kilometers while the coma is bright enough to map. Follow the chemistry across wavelengths that speak different dialects. Tie every moment to precise geometry so that models can learn the right lessons. Space carries the first burden. One infrared observatory opens its sun-shielded eye where Earth's air is no obstacle, and water bands cannot hide. Its instruments can separate carbon dioxide at 4¼ microns from the crowd, can follow carbon monoxide and water where the atmosphere below is opaque, can weigh dust temperatures by their glow rather than by reflection. Slits and integral field units target the head and the first arc seconds of coma, trading field for detail, tracing jets as velocity gradients rather than as faint fans. Moving target tracking keeps the smudge steady on the detector while stars slide by. The work is patient and exacting, and it turns a spectrum into a map that ties volatile release to specific directions in space. Another space telescope steps in with a talent for sharpness. Its ultraviolet camera can watch the OH band that water leaves behind, a proxy that still matters when water itself is hard to see. Its visible channel resolves the inner coma without the blur of air, deconvolving point spread functions until faint jets stand as thin ribs. Short sequences taken an orbit apart reveal rotation as a change in which ribs brighten. With careful subtraction, a limit on the nucleus emerges from the core of the light. Even a non-detection is powerful here. It tightens size bounds that ground-based images cannot match while the coma is full. Solar observatories add a perspective from the star's own domain. Coronagraphs that study coronal streamers catch the tail when elongation drives observers on Earth into twilight. Ion rays, disconnection events, and kinks that ripple after a solar wind shock all write themselves across frames taken for heliophysics. Those signatures become context for the chemistry. If a sudden change in tail geometry coincides with an outburst in gas lines, intrinsic and environmental causes can be weighed. If the change comes when the wind snaps, the file for plasma weather grows thicker and the file for vent drama stays thin. Ground-based instruments fill the spectrum around these pillars. Large optical telescopes work in Q mode, aligning slits to ride along fans and across the antisolar vector. Low and medium resolution spectrographs measure dust continua and the faint emissions of classic radicals that still whisper their presence. Polarimeters rotate through half-wave plates and filters to map how grains scatter and how their textures change with angle. Each image is tied to non-sidereal rates so that the head holds still and stars turn to streaks. Those streaks are masked and the remaining light pulled into apertures that grow outward to build radial profiles. Near-infrared spectrographs on mountain tops hunt low vibrational lines that rise from warm gas close to the vents. Methanol, hydrogen, cyanide, formaldehyde, and other quiet workhorses of comet chemistry appear there if abundance and temperature allow. Lines move with rotation and slit position, turning spectra into gentle wind vanes. Cross dispersers spread orders like a ladder, and sky subtraction alternates between dithered positions to remove the atmosphere's own glow. The result is a ledger of molecules that complements the space-based census at longer wavelengths. Radio and millimeter arrays bring the coma into focus as gas rather than light. Rotational lines of carbon monoxide and its cousins arc across receivers in bands where calibration is a craft. Interferometric baselines synthesize apertures large enough to resolve structure in the gas distribution. Velocity fields unfold as maps, blue on one side where gas comes toward the observer, and red on the other where it departs. If the map twists with time, rotation takes the blame. If it stays steady while brightness grows, vent geography rules. Isotopes sometimes show their weaker lines stacked across channels to lift them above noise. Even a limit on a deuterated species constrains the kitchen where ice is formed. Small telescopes make the heartbeat visible. A network of 1 meter and half-meter mirrors follows the light curve night after night, using the same filters and apertures so that seeing and sky do not masquerade as change. The cadence is relentless because rotation periods hide behind gaps. Data from mountains and deserts, islands and plains merge into a single curve that folds cleanly, or that refuses to fold and hints at tumbling. The same network watches for outbursts and for the slow drifts in magnitude that signal evolution in active area or dust properties as the sun grows stronger and then weak again. Twilight campaigns fight glare with technique. Short exposures avoid saturation near the horizon, while precise flats tame gradients. Stacks are built along the moving path to deepen the head without thickening city light. Specialized software fits a trailed point spread function to field stars so that photometry remains honest even when stars are lines. Guiders that usually lock on a fixed dot learn to chase a drifting speck. The result is not pretty to the eye, but to a pipeline it is gold. Those frames anchor the timeline across the days when geometry would otherwise close the book. Data travel as fast as the object. Ephemerides are updated nightly and pushed to observatories so that slews land on the target and slits catch the head. Alerts announce changes in brightness or tail morphology, and instruments that can pivot do. Calibrations accompany the data, because without flats and arcs and standards, the effort would dissolve into anecdote. Teams know that replication protects them from illusions, so independent reductions run in parallel. Where they agree, confidence grows. Where they do not, methods are inspected until agreement returns or a systematic is uncovered. Models grow beside the observations. Thermophysical codes propagate heat through layered crusts, predict which volatiles should wake at which distances, and produce synthetic light curves that change with spin and vent latitude. Dust dynamics codes release particles with size, distributions, and initial speeds, then let sunlight and gravity do their slow work. The output is cut into the same apertures used on sky and compared to radial profiles and color maps. Gas models start with simple assumptions about production and photochemistry, turning parent molecules into daughters and into ions, then into emission in the lines observers measured. Parameters are nudged until maps and spectra rhyme. Survey cameras keep watch on the wider scene. Wide fields that cover degrees at a time can catch faint old dust released months earlier, stretched into a ghost along the orbit. Those diffuse structures are nearly impossible to see on narrow fields. Deep stacks reveal them and trace synchrones back to times when activity changed. If a thin streamer peels away from the main tail at a small angle, it can be an archival marker for an earlier outburst. This retrospective glance adds depth to the narrative. The sky remembers longer than a night. A newer all-sky spectroscopic mapper will join this chore. It will visit every patch of sky with low-resolution spectra many times, laying a multi-epoch net across the near-infrared. A bright coma in its domain would be recorded as a sequence, not a single event, and that sequence would survive in a uniform archive. The benefit of uniformity is quiet but profound. Calibrations match. Backgrounds are predictable. Trends become real because systematics cancel when the system is the same. Engineers listen to this flurry because numbers turn into missions. If gas production follows a predictable curve with distance, and if outbursts seldom jump that curve, a fast, small spacecraft can bet on where brightness will be when it arrives. If radiance and speed suggest that approach, geometries often fall into a manageable corridor. A ready interceptor can wait in an orbit tuned for quick burns. Mission design eats statistics. Telescopes feed them. When the window begins to close, priorities shift to measurements that improve with fading. As the coma thins, attempts to separate the nucleus from its envelope return. Thermal observations at longer wavelengths try again to net the body's own heat. Precise astrometry in quieter dust refines non-gravitational terms and locks the outbound vector. The archive grows dense at the edges of the campaign for this reason. Ends are cheap in brightness but rich in clarity. The last act is curation. Raw frames land in public vaults where future teams can rework them with new methods. Spectra are posted with response functions so that line ratios can be revisited when better models arrive. Time series are shared with precise apertures and phase angles attached so that other hands can fold them anew. A brief encounter becomes a decades-long resource. The object leaves, but its measured light remains within reach of anyone curious enough to open an old file and ask a new question. Lessons gather like dew on a cool morning, clear enough to read if the eye lingers. The first is simple and deep. Volatile hierarchies are not universal. The familiar script that gives water the loudest voice near a sun-like star is only one arrangement. Another arrangement rises when colder ices find daylight through shallow seams, and then dust responds in a language of heavy grains and steady fans. Models that assumed a single driver must widen their stage. Energy balance remains the same arithmetic, yet the order of entry for each molecule changes the choreography of light, texture, and thrust. The education is gentle. The star teaches no new physics. The small world reveals new pathways through old rules. A second lesson concerns crusts. The skin of a nucleus is not a passive blanket. It is a machine of pores, welded necks, amorphous pockets, and cages that free or trap gas at temperamental thresholds. Diffusion through such a fabric writes delays and pulses into the coma. That same fabric edits the sizes of grains that escape, favors some vents over others, and stores stress that opens cracks on a timetable set by heat and rotation. Thermophysical models that once treated the surface as a thin valve learn to honor centimeters and millimeters, where capillaries and clathrates run the show. Small depths become large causes. Dust behavior forms the third page. A sunward wedge near the head, a stouter tail, ribs that brighten with a clock, all teach that geometry, grain size, and launch speed outweigh romance. Forward scattering fattens the inner coma. Orbital plane crossings stage apparent spikes, and radiation pressure shepherds fines while large fragments walk for a while against the light. Synchrones, syndines, and polarization maps become everyday tools rather than special effects. When they are used with patience, illusions vanish and mechanics remain. The reward is a coma that reads like a ledger, each pencil stroke a vector drawn by light and mass. The fourth lesson lives in faint spectral lines. Neutral atoms that shine without a matching chorus from their usual companions ask for new chemistry in cold places. Reactions on grain surfaces, fragile complexes formed under long winters, and the particular structure of the solar spectrum work together to bias what is seen and when. Atomic fluorescence yields to laboratory constants, yet the abundance of parent species yields to the invisible chemistry of microenvironments. The practical outcome is firm. Laboratory astrochemistry must expand beyond the classic volatiles. Metals in exotic hosts, photodesorption cross-sections for disordered skins, and pathways that assemble unusual molecules at low temperature belong beside traditional catalogues. Telescopes can only count what nature releases. Nature releases what its surfaces have already composed. Spin and torque write the fifth. Gas leaves where heat and shadow allow, and every jet pays its momentum into the nucleus. A small change in period across weeks is not noise. It is a seismogram from vents. Light curves that refuse to fold cleanly whisper of tumbling that long predates the present season. When rotation is placed beside limits on size, density bounds emerge that speak to porosity and cohesion. The safe margin from rotational break tells whether the body is a rubble pile that trusts friction, or a sturdier shard that trusts bonds. The lesson is practical. Dynamics measures interiors without touch. The sixth lesson steps back to count. A short list of interstellar bodies still sketches patterns. One nearly bare, one exuberant, one that wakes under colder chemistry. Together they prove that ejection does not prefer a single size or a single inventory. The space between stars holds many survivors, not one type of survivor. Population estimates remain humble, yet even humility draws lines on a chart. Discovery favors dust makers over stones, fast apparitions over slow ones, certain radiance over others, and those biases must be written into every rate. When that accounting is honest, the galaxy looks busy enough to supply regular visitors, and quiet enough that each remains a minor miracle. Seventh, the sky reintroduces itself as a galactic street rather than a courtyard. Velocities consistent with ordinary disk motion argue that the traffic of fragments belongs to the same kinematic families as the stars themselves. A single trajectory never names a house, yet it shows that exile is part of many systems. not a trick of a few violent neighbours. Gravity sculpts worlds and then exports what does not fit. The export drifts in streams that follow the spiral's wheel. In that traffic, a star that hosts oceans swims through a drizzle of distant chemistry. The exchange is thin, continuous, and older than any calendar. Eighth, the craft of observation grows sharper under pressure. Trailing losses are met with short exposures and motion-match stacks. Twilight becomes useful time rather than wasted glow through careful flats and path-following sums. Mid-infrared line work leaves the air and finds space, while near-infrared roams high mountain windows in disciplined cadence. Interferometers map gas as a field rather than as a scalar, and polarimeters assign textures to dust rather than colors alone. Each technique carries its own cautions, and those cautions are repeated often enough to become muscle memory. Standard stars, stable response functions, shared apertures, and public archives turn a quick campaign into a durable record. A ninth lesson folds technology back into intent. Rapid target of opportunity pipelines, modular reduction codes, and open alerts erase distance between teams. When a faint feature appears in one instrument, others can pivot and test it within days. Disagreements appear early and are treated as instruments talking to one another, not as rivals. The culture learns to privilege replication over flourish. In that culture, small signals survive scrutiny and false novelties fade without drama. The visitor becomes less a headline and more a shared laboratory. 10th, engineering listens. Interceptors ask for the statistics that determine whether a sprint can meet a target with fuel to spare. Staging orbits that widen the window depend on the rate and radiant distribution. Spectral lessons about vent behavior and torque inform how close a probe might safely fly and what sensors to trust most in a brief pass. Even without a rendezvous, a flyby that arrives during a peak in activity collects more truth than one that misses by a week. The science becomes a map for motion, and motion returns better science. The feedback is healthy. Beyond methods and numbers lies a human lesson. Surprise is a teacher only when discipline answers. The object neither courts affection nor invites myth. It offers a set of measurable consequences to sunlight, vacuum, and time. The response that rises to meet it is not wonder alone, though wonder moves the hands that turn domes. The response is a catalogue of questions written as exposures and spectra, and a willingness to let arithmetic change what was hoped. Confidence yields, yet it does not collapse. It reshapes. The visitor also tunes philosophy. If chemistry can flourish in cold, build complexity in darkness, and travel for ages on a rock the size of a town, then the ingredients for rich worlds are broadly available. That availability does not promise outcomes. It promises opportunity. The galaxy looks less like a chain of isolated workshops and more like a linked set of kitchens, each shedding a little flavour into the common air. The scale of exchange is small, the dignity of local histories remains, and yet a thread connects them. Finally, the most modest lesson is the most durable. Precision is kindness to the truth. A curve fits or does not. A line repeats or it fades when the calibration changes. A lobe that points the wrong way explains itself when size distributions are honest. A strange ratio earns time in a laboratory more than a headline. When this posture is kept, arrivals from other suns stop being occasions for arguments about novelty and become invitations to refine a common craft. The sky will deliver more guests. The work learned here will not be wasted. What the traveller teaches, then, is not a single revelation but a change in posture. The field lowers its shoulders into a broader stance. It keeps the familiar equations, rewrites some boundary conditions, and invests in wavelengths and methods that once sat at the edge of the budget. It remembers that small worlds carry large stories if read with care. It accepts that the traffic between stars is quiet and constant. It adds a line to a long book that will be read most clearly when many such lines exist. For now, the page glows, the ink dries, and those who watched return to their instruments with a better ear for the next voice that crosses the dark. Faintness arrives like a custom of the sky. The tail loosens into a veil, the veil dissolves into a smear, and the smear thins until only a slightly swollen point remains. Telescopes that once chased structure now settle for steady integrations that prove the object is still there. Exposure times lengthen. The air shifts from the bright hush of anticipation to the softer quiet of work that knows it is ending. The path is drawn clean on ephemerides. The curve continues to open. Gravity's nudge grows less persuasive with every hour of distance. What was once a local weather of gas and dust becomes a geometry again, a line that remembers a star and heads for nobody in particular. Cooling takes command. Sublimation slows until it reads like punctuation rather than speech. The coma contracts toward the nucleus, then yields to the vacuum. Outgassing terms in orbit fits relax towards zero. Jets that once braided the inner few thousand kilometers unclasp into nothing. Dust that was launched when the light was stronger keeps its promises a while longer, streaming into the anti-solar night with the patience of stones and flakes that listen only to light and gravity. Far behind, synchrones write faint ledgers across the orbit, readable to those who stack enough sky and subtract enough noise. A season of energy has spent itself. The ledger remains. Data refuse to recede. Servers hum. Archives accept their cargo with indifferent diligence. Deconvolved cores and long slits labelled to the arcsecond, flats and arcs and standards with their dates intact, time series wrapped around filters and apertures, all of it lands in public vaults. There it will sit, ready to agree or disagree with the next interpretation, ready to surrender a new pattern when calibrations improve. A quiet faith lives in the filing of such light. Later, under different questions, the same photons will speak again. The tail that once leaned across sky charts becomes a set of numbers that describe departures. Inbound and outbound asymptotes draw a small angle that can be written on paper without drama. It is enough. That angle pins the outbound vector. The vector becomes a sentence about where the traveller now aims within the wider drift of the local stars. The sentence is short. It is also the only one that can be written without embroidery. There is comfort in such limits. They make the known crisp and the unknown honest. The body itself returns to secrecy. Inside the shrinking coma, fractures that once breathed begin to seal with frost. Thermal tides soften. Stress relaxes across welded necks in the crust, leaving hairline cracks that no longer reach daylight. Rotation continues with the same clock unless tiny talks have written their whispers into the period. If any change remains, it is a quiet adjustment rather than a confession. Interiors that were guessed at remain guessed at, bounded by light and heat but not resolved. The dignity of what cannot be seen has not been insulted. Questions do not vanish when light does. They sharpen their edges as if absence were a magnifying glass. How thick is the varnish that filters heat and gas? How deep do clathrates and amorphous pockets extend? What is the bulk density hidden behind the upper limit on size? Which isotopes would a longer campaign have balanced with tighter errors? Which metals would have joined nickel given time and wavelength? None of these are confessions asked of a receding dot. They are promises written into planning documents for the next opportunity, the next worldlet with a similar temper or a different one. A field advances by this kind of patience. It allows endings to be endings without pretending that they are failures. The sky changes mood in ways that instruments register and people feel. The night that held a bright fountain near a star returns to the usual disciplines. Planets keep their hours with their old reliability. Deep fields remember their catalogues. Telescopes hand their time back to slow programs that will feed discoveries measured in years. In control rooms, bulletin boards that once bristled with coordinates lose their urgency. A few notes remain. Reminders to re-reduce a set once a new response function is posted, or to check a subtle color gradient against a different phase law. It is a graceful release rather than a withdrawal. Work moves where the light points. Meaning is not an instrument, but it keeps company with them. A transient from beyond the sun offers a style of lesson that belongs to endings. It shows that belonging is sometimes brief, and that knowledge can arrive only to recede. It argues, without rhetoric, that openness, not closure, is the scale on which many truths are weighed. Children look up at a sky no different from last year, and know it is different because they now know what a hyperbola looks like. Students learn that patience and speed can share a single campaign. Practitioners learn that a careful archive is a kindness to the future. Each of these learnings survives brightness. There is a ritual tone to the last observing logs. Sky conditions, instrument configuration, target acquisition, integration times. A brief note that the object is now fainter than a standard star that once made calibration easy. A suggestion that this will be the final night unless a surprise returns. Then signatures. The ritual is not nostalgic. It is how a craft ends a task with respect. A few weeks later, a plot appears in a preprint. One more point placed on a curve that describes fading. The point does not change theory. It completes a line. Completion is a kind of truth. At scales larger than a star and a season, the receding fragment carries the same calm logic. It leaves with more energy than the sun could take and gives back a small change in direction as a receipt. It glides into a galactic flow that ignores the affairs of single worlds. Starlight dwindles to a thin memory on its skin. Radiation resumes its long patience. Slow chemistry turns again in dark pores. Tides of nothing pass through its frame as it crosses braided regions of the disk. Somewhere, many years from the night of fading, another star will announce itself faintly on the horizon of that small surface. The same physics will enroll the same little body in a new story with a new set of readers. Imagination prefers to attach beacons to such travellers. It attributes messages to speechless things. The more telling truth is quieter. A fragment like this knits examples into a pattern. It makes interstellar space feel less like a clean emptiness and more like a hallway where dust scuffs the floor. It reminds the mind that distances do not erase materials or their histories. It also reintroduces comfort with not knowing. A non-answer kept in the open is often a better gift than a tidy claim. Instruments can stand under such a gift without embarrassment. The last human act in this episode is small. Someone closes a dome. Someone clicks an upload. Someone labels a set of flats. Someone locks a lab door and walks home along a path that smells faintly of warm metal and cold air. That person will return to a different sky and another plan. The object will not return. Endings teach their own resilience. Those who read the light know how to keep moving while they wait for the next visitor to draw a curve that does not close and to breathe a chemistry that rearranges habits. The sky becomes ordinary again, and ordinary is not a step down. It is the stage on which the rare can be recognized when it comes, and on which patience can accumulate into an ability to listen. The last images of the fading tale keep their place in an archive the way a last footstep keeps its place in sand. An onshore wind may soften it, a new tide may write over it. The sand remains, ready for more steps. In that readiness is the real closing, not a door, but a floor. Night returns to its slow grammar. Desert air cools around domes like a steady hand on a fevered brow. On coasts, sea breath moves under stars that hold their positions as if they had not watched a visitor pass. In lonely valleys, radio dishes lean away from day and listen to the rustle of the galaxy, a sound made of no sound at all. The world sleeps according to local customs, while the small body, now only a number, moves through a dark that has never learned the names of places. Gravity is still the old curve. Space is still that soft geometry that Einstein drew with patient chalk. A fragment chooses neither doctrine nor defiance. It follows the page as written, adding only the colour of a crust and the schedule of a spin. The page becomes a story because living minds read it. Hawking once described horizons as places where information refuses to return. A hyperbola is a horizon of a different kind, a line on a map that will not loop back to its starting word. Yet information does return. It returns as spectra and profiles, as slow ideas lifted out of a brief blaze. The habit of reading such light is an act of care. A society that funds, mirrors and training networks and archives, gives itself the gift of knowing how to ask useful questions when rarity allows. That discipline spills beyond the subject. It teaches how to accept absence without surrendering curiosity, how to revise an assumption without losing nerve, how to leave an answer open long enough for a better one to find the door. The sky does not care whether these habits settle in minds, but minds care, and the caring spreads. Somewhere a child will look up and learn that motion is a language. Somewhere a quiet clerk will file data that a future graduate will need. Somewhere an instrument builder will write a line of code that saves a night, and no one but a handful of colleagues will know. In such grains of work, galaxies turn into neighborhood weather. The small completes the large. The visitor is gone, and yet the thought remains warm to the touch. Sleep can carry it gently into morning without breaking it. The next dawn will put birds in air and dust on roads, and sky above all of it as patient as ever. The thought will still be there, a soft ember that says the universe is not only vast, it is attentive to small things, and that attention can be learned.